Hello, my name is John Lynch. I'm a senior software engineer at Side Effect Software, and this is a masterclass on advanced Vellum workflows. The goal of this class is to go through some more advanced techniques in the Vellum Solver that's new in Houdini 17. In particular, we're going to look at changing the setup of the simulation over time during the simulation. And this can be from something as simple as pinning or welding geometry together while it's running, or animating the constraint properties, to possibly even creating new constraints over time and breaking them due to the amount of stress or stretch on those constraints. We're going to also talk about some of the more advanced features of Vellum, like plasticity, and also look at soft bodies and grains within these same workflows. So this is an overview of the topics we'll be discussing in this class. I wanted to start with a discussion of some of the internals of the Vellum Solver. And these are generally topics you don't need to think about too much if you're just doing basic cloth sim or hair sim. But as you start to get to more complex setups, or possibly try to debug simulations, trying to figure out why things aren't looking exactly as you might expect, it's really useful to understand a bit more about what's going on underneath the hood. So we'll talk about what XPBD is, the Extended Position-Based Dynamics algorithm, and how Vellum represents data, the difference between first and second order integration, what that even means, and what that means for the simulation, graph coloring and how that affects solver performance, what graph coloring is in the first place. And we'll also talk about the solver iteration choices, the parameters there that control different aspects of the simulation, both for collisions and constraint solving. Then we'll move on to pins and welds. Pins are a way to hold geometry in place. Welds are ways to attach geometry together. And we'll also discuss the difference between hard geometry attribute-based pins and welds versus using constraints, which are soft and act more like springs, and as well as how you might break those pins and welds either programmatically or as a result of stress or forces in the simulation. We'll talk about how to animate constraint properties during the simulation, how to create new constraints dynamically, as well as breaking those. And then we'll talk about some of the more advanced features of Vellum, like plasticity and soft bodies and grains. So the Vellum Solver is an example of a position-based dynamic solver. And we've had one of these in Houdini for a few releases now in the Grain Solver. And the Vellum Solver is sort of a continuation and extension of the Grain Solver in a lot of ways. They're similar in that they operate on constrained particles. So you have what essentially looks like a pop sim, a particle simulation, except you have the addition of all these constraints that determine how the various particles interact with one another. And you can use those constraints to make things like cloth and hair and soft bodies and all these things that Vellum supports. And an important aspect of the way you represent this data, similar to the Grain Solver, is the particles and the constraints are just geometry with attributes. So the particles are just points. They have lots of attributes that represent the dynamic state of the simulation. And the constraints are also just primitives that have attributes as well. So things like stiffness and rest length. And all of those things can be manipulated with all of the sort of regular SOP tools that exist in Houdini. So Vex, Wrangles, Attribute Create, Attribute Randomize, any of those tools, multiple tools that we have for manipulating attributes, can be used on the dynamic state of the particles or any of the dynamic state of the constraints as well, which ends up being really powerful. All of these constraint types are configured in SOPs with possibly chained Vellum constraint SOPs. And these are all, for all the various types of constraints that Vellum supports. The solver itself is just a Houdini digital asset, like a lot of solvers in Houdini. And so it's microsolver based, meaning it's a bunch of split up into a bunch of solvers within it that each do basically one operation. The constraint solving is done with OpenCL, usually on the GPU. The collision detection resolution is done with the detangle SOP, which is C++, but everything else is pretty much in Vex. So the particle and constraint logic is in Vex. In particular, things like breaking and plasticity and updating from rest geometry is all in Vex. So it's a sort of thing that if you really are sufficiently motivated and interested, you can find the Vex code that does all of these things and really understand more about exactly how those operations work. So position-based dynamics is a fast, stable method for solving constrained particles like we talked about. It's GPU friendly. So especially if you find a good way to separate up the constraint primitives so that you can solve them all at once on the GPU without any conflicts, which is what graph coloring does, then you can get really fast constraint solving on the GPU, and we'll talk about how we do that. You've probably seen this before, but the basic position-based dynamics algorithm, at least for first-order integration, is to store the original position of the particle, and you take one step forward, given its current velocity. So that's the p equals p plus v times the time increment. Then you update the position to satisfy all the constraints, resolve any collisions, and just calculate velocity based on the change in that position. The first order integration approach shown here has some issues with things like damping out the energy in the simulation. And we'll actually look at that in just a second. There's actually some other sort of more sophisticated options within Vellum, but this is the basic algorithm. And on top of that, Vellum actually implements the extended position-based dynamics algorithm, which is sort of newer research. And the three important things it gives the solver are iteration and time step and variance stiffness. And so what that means is it's an iterative solver, but if you find out that you need to, for instance, you have very fast moving collisions, so you have to take extra sub-steps, it won't actually go to infinite stiffness, which was a problem with position-based dynamics. Essentially, all the constraints were sort of infinitely stiff. But if you want something like a spring that isn't very stiff at all, then you want it to, no matter how many, if you take a huge number of iterations because you have super fast moving collisions, you need lots of sub-steps, you don't want the behavior of the simulation to change. I should point out that this is true as long as you've got enough iterations in the first place to actually converge to the proper solution. So it's not going to magically make it so that you can only use a couple of iterations and everything gets solved. But once you use lots of iterations, if you have to, because of things like fast moving collisions, you're still going to get the same behavior. It also provides per constraint damping, which is really useful to dial in particular looks. And it also gives an estimate of the work done per constraint, which we call stress in all of our user interface elements, which is a little bit of a misuse of the term, but it can be really useful for some effects like braking, and it's also just really useful for visualizing where the work is being done by all the different constraints. So now let's jump into Houdini and look at how Vellum represents its simulation data. So to set this file up, I just created a very simple grid and chose the Vellum cloth tool to set it up as cloth and a torus object, and used the surface collider tool. So if we go into the AutoDOP network, we'll see that we've got this primary object here, and then we just source the geometry data into it. And this is how POPs works, how the grain solver works. And so again, you're seeing that the Vellum solver is really a continuation of those ideas. And the data itself, the DOPS data itself, is stored in two separate pieces of data off of the main Vellum object. So the geometry is, again, this is like the particle data for POPs. And it stores what is basically the dynamic state of all the points within the system. So you get things like position and velocity and p-scale, or the size of the particles and their mass. And over time, you can see the solver is essentially updating the dynamic state of all these attributes. And it's doing them in accordance with these constraints, which are represented over here. So you'll see that there's points here, but they're actually just corresponding to the same number of points that are in the main geometry. So there's 900 points in each one. But there's actually no attributes here, or no attributes except for position, which has to be there. All the data is really stored in the primitives, which are the constraints themselves. So if we get rid of this, and we want to see things like stiffness and damping ratio and type and stress, for example, we can see all the different constraints types. There's bend types, and there's distance. They all have, and we should add rest length for that, and they all have a rest length. And the stress here is what we were talking about before, which is part of the XPBD algorithm. It's basically an estimate of how much work each constraint is doing. It's kind of an output variable or attribute from the solver. So all these, typically in the most basic simulations, all of these attributes are going to stay primarily constant, but the stress is going to be updated with estimates of how much work these constraints are doing. We can actually visualize that over here. If we go to our guides and show guide geometry, we can have like stretch stress, for example, or the bend stress. So this is how much work is being done by the bend constraints. So we can see, in the sort of higher bend areas, there's more work being done by those constraints to try to keep things flat. Although we have very low bend stiffness, so they're not really doing that much work. But you can see where those constraints are operating. And then if we go to where this was actually set up, which is in the grid object. So if we look at the Vellum constraint SOP in the first place, this is where that data comes from. we have two outputs from the Vellum constraint SOP, and the first one is the geometry, and the second one is the constraints. And again, we're just seeing that this corresponds to that same data that then just gets ingested into DOPS. So as we change things on the Vellum constraints SOP, things like so let's go look at we can change things like the P scale, the thickness, change the mass. And if you notice, things like pinning a point also can have an effect. It can do things like setting the mass to 0. So, and we'll talk about a lot more about what pins actually mean. But so this is actually saying that if with the mass of 0, this point actually can't move. And then the constraints themselves, similarly, as we do things like change the rest length scale, we'll see the rest length change as well. That's being stored here. So basically, the Vellum constraints SOPs are ways to create this data in the first place and then manipulate the attributes that control the simulation, and with tracking both pieces of geometry, both the particles and the constraints, the particle points themselves, and then the constraint primitives as well. Now, we've talked about the data that the Vellum Solver uses to represent the simulation, and I wanted to talk now about the integration methods that are available inside Vellum. And there are first order and second order accurate options. That generally refers to just how accurate they are, with second order being a lot more accurate than first. And I wanted to explain what we even mean by integration. So the goal of what's called numerical integration is to move the particles before we solve for constraint to collisions, and to compute the velocity afterwards. So if we look at the algorithm we had here, it's basically this step where we update the position before we solve, and then this step where we compute the velocity afterwards. First order integration uses the velocity at the beginning of the time step, and it takes a linear step. And that's generally fine. The problem is it just does a not very good job of predicting where the particles are going to end up when you have nonlinear motion. And constrained particles very frequently, almost always, have nonlinear motion. Sort of by definition, they are attached to something else, to another particle, to a pin, something, where they're moving in some sort of curved motion, or at least nonlinear. So what happens is we will take the first order integration takes a step that is not very close to where it's going to end up after the constraints are solved, and we end up losing energy that way, and the constraints will end up taking longer to converge, which means you need more iterations to combat against stretch and things like that. So you get a less accurate simulation, and it takes longer to solve, which isn't a great combination. And the reason we care about energy in the simulation is energy turns into things like flapping cloth, or a flapping flag in the wind, or fine wrinkles in cloth. So it's basically losing detail because it's not using an accurate enough prediction of where the points are going to be. Second order integration does a better job of retaining the energy because it uses the previous time steps, position, and velocity to do a better job of predicting nonlinear motion. So the initial position of the point before the constraints are solved is going to be closer to where it's going to finally end up once the constraints are actually solved for. So we lose less energy, and we will converge faster, which means we can get away with fewer iterations. The downsides are it requires storing that extra time steps worth of position and velocity data, and it can, in some situations, cause bouncing artifacts, particularly with collisions. I want to demonstrate that and talk about how we can get around those problems. Okay, so we're in Houdini with a very simple setup here. This is just a line that has 10 points on it. It's a meter long. And we set up constraints on it to make it act like basically like a stiff rope. It's got string constraints. So it's got a distance constraint that makes sure that each one of these line segments retains its original length. And then it's got a constraint on each of these angles to make sure that they stay something close to straight. So it's like a stiff rope. And then the Vellum Solver itself, this is the SOP version of the Vellum Solver. And we've just turned off collisions. We've turned off this wind drag or air drag. And really that's it. We're also visualizing the stretch ratio. So if I hit play here, you'll see that it's actually retaining a lot of this energy. If we retained all of our energy, we'd start here and we'd end up over here. But we're pretty close and doing a pretty good job, and there's very little stretching happening with the second order integration. If we switch to first order, you'll see we lose a lot more energy, it damps faster. And then at the beginning, we also get this stretch through here. So this section here, we're actually getting a fair bit more stretch. And that's a result of the fact that we're doing kind of a worse job predicting where the particle's going to be before we solve for constraints. So if we look at the attributes, this is what I was talking about before. We've got this sort of P previous and V previous are just the velocities at the beginning of the time step. And then we've got the position and velocity at the end of the time step. This is with first order. So there's a little extra data, but not too bad. Once we switch to second order, we actually get yet another copy. This is this last and V last, P last and V last, which are from the previous time step. So if you're looking at the output of the Vellum Solver and wondering why you have nearly identical copies of your position and velocity, this is why. If you are using something like the Vellum IO SOP to save your geometry and constraints to disk, which is a good idea, it's already got a default for your save filter to delete a lot of this stuff. So a lot of this stuff won't go to disk. It really just takes up memory while you're doing the simulation. And there's a little extra computation involved in this more accurate integration. On the other hand, compared to solving for collisions and solving for constraints, it's really negligible. So it's not worth worrying about too much. So if we want to see why this works the way it does, I've got quickly a couple of different Vellum solvers here that I've just modified to, this is right here is the sort of constraint and collision loop. Right here, I just am copying the point position into this P pre attribute. So we're just saving the predicted position before all the constraints are solved. And so what we're viewing here is really the templated line is where the integrator predicted it to be, and the points are where it actually ended up solving after the constraints. You can see there's a fair bit of error here. As it moves down, it's essentially not doing a great job. It's okay of predicting where the point should be. If we view the second order, we see there's a good bit less error, about half the error. And that actually adds up over time pretty significantly. So that's why it's more accurate. It turns out that if we go back to this one and increase our substeps, so we're doing more substeps, we're doing fewer iterations per substep, so we're ending up doing the same amount of iterations per frame. It turns out that the substeps makes the integrator, especially the second order integrator, even more accurate. So you can actually see we're keeping pretty much all of the energy in the system as we solve. So if you move to more substeps and you're noticing that your cloth seems a little more energetic, a little flappier, a little or whatever, this could be why. It is actually getting more accurate in solving for the system, but it just, in case you're a little bit surprised by that, that's why. If you find out that you have too much energy here, the answer is almost never going to be to switch to first order, because again, you're going to have your constraint solving much slower. So generally what you're going to want to do is compensate with air drag or some kind of drag. So because again, you can put per constraint drag as well, but this is generally a good idea. So if you'll notice, if we turn this on, very quickly all of our energy gets damped out of the system. We don't get any stretching or anything like that, but we lose the energy very quickly. So if you've got cloth that you're trying to make slow down in the air, or hair to slow down in water or something like that, you're much better off sticking with second order and using these using some sort of wind drag here. So second order sounds great and all. Why don't we always use it? Well, we really do always use it. It's the default, but there is a problem with it. And I'm going to demonstrate that real quickly. So we've just got a piece of cloth here that is falling down on this sphere, and it bounces like crazy. And that kind of looks awful and very unrealistic. And so what's going on here? On this Vellum Solver, I've got second order enabled, but I've turned off this max acceleration choice here. What this does is, as the cloth is falling down, it's basically predicting the position of the next for the next time step. But if we come upon a collision where we've got this very discontinuous change in motion, it does a really bad job of predicting where that point's going to be, and it ends up predicting basically a big bounce. So what we can do is turn this max acceleration option on, and in particular this fallback to first order integration on collision. So what this does is it checks to see if there was a collision. If it is, it compares the acceleration that's about to occur to this fairly high number. So this is about 10 Gs. And if it exceeds that, then it'll just use the first order estimate. And what this does is gets rid of most of the bouncing. So this number is possibly a little high, this max acceleration number as a default. So if you're seeing bouncing, especially with one substep, you can move this down to say 20, still 2 Gs, and you get a whole lot less bouncing. You still get these sort of, nice little wrinkles in behavior here, but you don't get that big bounce on the initial stop. So what the solver is doing is actually setting this fallback integer attribute here. So we can actually click on that to set a visualizer, and you can see where it's happening. So basically it's happening where it hits the sphere there. So we're falling back to first order there. And then we're falling back when we first hit the floor. But from then on, it is in collision, but it hasn't gone past this acceleration. It's getting still fairly smooth motion because it's just sort of sitting here almost at rest. So we're still getting the second order accurate, which is nice, even though we're in collision. So the other option, of course, is to just switch to first order. The reason that's not so appealing is you get this kind of very damped looking kind of sim out of it. So we don't get those nearly as nice wrinkles as we had before, and it's just not as good looking a sim. So the default is to always use second order and to keep this max acceleration on. If you see some bouncing, it's probably possible that this default is a little high. So you can set it down to 20 or even 10, and you should generally get much, much less bouncing that way. The next topic on Vellum Solver internals is graph coloring. And I wanted to just discuss quickly what graph coloring means and how it's done within Houdini, and then how it's relevant to the Vellum Solver, and in particular, how it affects performance and how it can give you some insight into how the solver is going to perform with different types of constraints. So there's a new SOP in Houdini 17 called the graph color SOP. And what it does is it segments primitives into independent sets. And these are usually called sets of different color. It's a graph coloring or graph theory term. So it's implemented actually in OpenCL. This algorithm is it's greedy, parallel, and iterative, and we'll actually see where you can see the code. It's just written as a kernel within an OpenCL SOP. And once it's done its work, the primitives in each color set will share no points. So what that means is each primitive that is in this set will share no points with any other primitive that's in that set. So if you take a bunch of primitives in a particular color and send them off to, for instance, the GPU, you know that you can be safe updating all of their point positions and there won't be any conflicts. So that's why you do graph coloring, is it basically makes it possible to process large amounts of primitives that are connected in parallel. And that's exactly what we have when we set up a bunch of constraint primitives. So once you've turned these primitives, or you've assigned colors for all of these primitives, the number of colors corresponds to the number of GPU batches. So basically, we're going to send off each set of colors to the GPU and process it all at once. And in general, you want lower numbers of colors because you want lower numbers of GPU batches. Just a fewer numbers of times that you send kernels to the GPU is better. The other relevant thing for Vellum is that it's faster to sort all these primitives by color, so that basically you're operating on them next to each other in memory. So you'll see where we do that. And that's actually relevant to operating with constraints within Vellum, because the order that you send them into Vellum is maybe not the order that you see them if you're looking at them within the actual solve, because they've been resorted when this graph coloring operation happened. Anytime that we change the topology of the constraint, so let's say we add a bunch of glue constraints dynamically to glue a bunch of hairs to a piece of cloth or something like that, that basically means that the number of independent constraints has changed, and the topology of that has changed. So we actually need to recolor every time that happens. So within Vellum, there's a fair bit of intelligence to track the topology, including welding, and we'll see why that's important later. And it recolors whenever that changes. So in particular, it means that we don't really want to be sending in entirely new sets of constraint primitives all the time into Vellum. If we want to change some aspect of a constraint, we're better off just changing that one attribute within the solver itself, rather than trying to import a whole bunch of new primitives every time step, because every time then it would have to be doing that recoloring, which can be expensive. And so you'll see that any of the operations that affect topology in the Vellum solver, in particular breaking constraints, has options to either operate each frame or each time step. And that's because sometimes you can't really tell the difference between if you break something at a sub-step. But if you are recoloring every sub-step because your topology's changed, it can actually slow the solver down. So we give a frequency so that if you want, you can only break, for instance, each frame, because you may not tell the difference in terms of how it looks, but you will notice the difference in terms of performance if you, say, have 5 sub-steps and you're recoloring the graph all the time. So let's jump into Houdini and see what that looks like. So here's a very basic example to demonstrate graph coloring. We've just got our basic squab here that we're going to run graph coloring on and look at the results. So here's this graph color SOP that is introduced in 17. And as I mentioned, it's actually implemented as most of the algorithm is in OpenCL here. So it's a parallel greedy algorithm. It's kind of an interesting bit of code if you want to have a look at it. But it's generally quite fast. But we're going to look at it. It's because it is iterative, and normally this max iteration defaults to like 20,000, and it just exits out as soon as it's colored the entire set. So it usually takes maybe 100 iterations. But we're going to actually set it to the frame number so we can watch the coloring happen as we play the frame bar. So what this will do is we'll actually create a color primitive attribute, and then we're just assigning a random color for each one of those based on that attribute. So if we hit play here, we can sort of watch the coloring process or coloring algorithm execute. And as we get to about frame, looks like about 130, we've well, not quite yet. So yeah, so about 140. So about 140 iterations to color this. So as I described before, if you look at these, like this primitive here, for instance, has a color that is different from all of the primitives around it that share points. So all these primitives here share points with this one in the middle, so they all have different colors. The next one that has the same color is going to be this one here, and you can see its points are independent, as are this one's, and the same thing happens with, for instance, this blue one. So what this means is that we can operate, for instance, on all of these green primitives, on the points for all these green primitives at once, and we know that they're not going to conflict. And then we can do, for instance, all the blue ones, and we know they won't conflict, and so on for the kind of gray and the dark green ones here. So that's generally why we want to graph colors, because it lets us then do interesting parallel algorithms on the points for each set of primitives. So we're doing another thing here, which is we're sorting the output primitives by color, and we're creating these two different sets for detail attributes that are called work sets. And these work sets we can actually send off to OpenCL, and they actually keep track of these sets of different colored primitives. So there's actually an OpenCL SOP and DOP mode where they can read these work sets and operate off them in parallel on the GPU. So that's why we run this and why we create these output attributes. And if we look at the results of these, so we can see that we've got 8 different colors here, 8 different work sets basically. And we can see how big each one of them is, each one of these sets. So they start off fairly large. They end up, the final one, there's only a few primitives in that last work set there. And we can look at sort of the average size is around 600. So we could send this off to the GPU and process it in 8 batches essentially. And most of these batches are pretty good size. We're going to sort of tail off towards the end there. But in general, we would get good performance operating on something like this. The other nice thing about graph coloring, so you can imagine if this was a set of constraints, for example, we'll actually look at that example real quick in a moment. But let's say that this represented some cloth here, and then we wanted to have copies of it. So let's make, say, 4 copies. So we had 4 different independent pieces of cloth, for example. Well, you'll notice that these will actually color it the same way, and they'll actually color to around the same number of colors, actually the exact same number of colors. So they'll both have 8 colors. So what it does, it realizes these are all independent, and so it will actually do that partitioning for us as part of this coloring operation. So what happens is now we have the same number of batches, they're just bigger. And that's interesting because the GPU in general works really well with more data. In a lot of cases, you'll find that if you send 1,000 items to a GPU to process, It's fast, but if you then send 10,000 items, it's not much slower. It's certainly not 10 times slower because the GPU wasn't even saturated. It wasn't doing all the work it could do when you send it 1,000 items. So if you've had much experience with Vellum, you'll sort of find that if you send it some sort of medium resolution cloth, one piece of medium resolution cloth, it's quick. But then if you send it 10 pieces of that same medium resolution cloth, it only slows down a little bit. And that's actually that this is why, because essentially we're sending more and more data to the GPU, more and these larger batches to the GPU. There's of course a limit. So as you get to maybe 100 pieces, it is going to start to slow down. But in general, the fact that we can get these sort of automatically partitioned bigger and bigger batches is really nice for performance. So if we send this geometry into an actual Vellum constraints to cloth, to create the cloth constraints and color that instead, you'll see it's essentially doing the same thing. So this is actually what we'll be really doing for Vellum is all these different, for instance, distance constraint, all these different constraints will get colors and they'll be put into these different batches to be sent to the GPU. And you'll notice there's a lot more of them. So once you have all these networks of constraints, they actually get a fair bit more complicated. So you'll have more batches. And for instance, here again, because we've got these multiple pieces of cloth, we've got fairly big batch sizes across here. 27 of them. If we disable the copy, we've still got 27. It's just smaller batches. So that's just what I was describing before. If you look at something like hair here, and we color the results of that, these are actually really cheap. So we can see that essentially because the topology of this hair is so simple, we end up with only 4 batches here. So this is very fast to send to the GPU. The constraints themselves for hair are actually fairly complex, but because we can batch it up into such a small number of batches to the GPU, it actually gets really nice performance. And as we move to lots of hair, so let's say we move to 500 hairs, all that happens is these batches get bigger. And this is really why Vellum can solve hair very quickly, or at least from the constraint solving perspective, because it's a fairly simple operation in terms of number of batches that need to be sent to the GPU. The constraints themselves are expensive, but they're batched up very efficiently. On the other hand, if you look at something like a tetrahedral constraint, so if we tetrahedralize that squab and create distance constraints along all the edges and create internally a bunch of tetrahedra that we're going to maintain the volume of. So this basically makes a squab soft body. And we graph color that. We'll see that we have 80 batches, which is a lot. So, and the reason is if you look at some of these internal points, they're affected by a huge number of constraints. So all these constraints, all these distance constraints along each edge, all of the volume constraints for each one of these tetrahedra. So that's why these can get a little more expensive. Again, the constraints themselves aren't that complicated, but there are a lot of batches to be sent to the GPU. As you create more and more of these, you have the same number of batches, they just get bigger. And then finally, I just wanted to show you where that option on the Vellum Solver is right here, this breaking frequency. That's why we can turn it off completely, but then you have per frame and you have per substep. And again, this is just for performance. Because we have to graph color every time we change the topology, and you may not notice if you don't actually break every single substep, you can choose how you want that to work just for performance reasons. For the final topic of Vellum Solver internals, I'd like to talk about solver iterations. So Vellum is an iterative solver, which means that it's solving constraints over and over again, as well as solving collisions over and over again. And in general, the more iterations it has to do that, the more accurate it's going to be. In particular with constraint iterations, if you don't give it enough iterations, you're going to see stretching in cloth or springs, or insufficient stiffness for things like bending. In general, if you need more stiffness, or if you're moving to high resolution geometry, you're generally going to want to increase those constraint iterations from the default. As we saw from the integration examples earlier, substeps are actually better than just increasing the constraint iterations, because you're actually going to do a better job in the integration step of predicting where the final position is going to be, and it's a smaller time step. So the constraints actually have to do less work. So you're probably better off in terms of accuracy using 5 substeps and 20 constraint iterations rather than 1 substep and 100 constraint iterations. But it is going to be more expensive just because each substep has more to do. Collision iterations, usually with a detangle SOP, are interleaved with the constraint iterations at a lower frequency. And so what that means is at the default of 10 collision iterations and 100 constraint iterations, for every 1 collision iteration, the solver will then do 10 collision iterations. So the collisions are like the outer loop, and they will generally run at a much lower frequency than the constraint iterations. And you'll maybe have 10 of them while you might have 100 or 200 constraint iterations. And the reason for that is mainly just performance. The detangle SOP and collisions in general are just very complicated and time consuming. So in an ideal world, you would actually be able to run those at the same frequency, and we'll actually see an example where that starts to become more important, or at least getting those frequencies closer. So you'll need to increase those collision iterations when the collisions are fighting against constraints or other collision objects. So, and again, we'll see an example of needing to do that. And finally, there's smoothing iterations. And smoothing iterations are there to smooth out any constraint error. So smoothing iterations are, again, for constraints. And they're to smooth out error for impossible configurations. What I mean by that is situations where you might have infinite stiffness on, say, some spring constraints or distance constraints, but then you're trying to stretch them over a collision or just with 2 pins on either side. And there's basically no way to accurately solve it. So you're going to get some error, but you want that error to uniformly spread across the geometry. And this is what smoothing iterations helps you do. So from a more technical perspective, smoothing iterations are a Jacobi way of solving the constraint versus the Gauss-Seidel, which is the default for constraint iterations. And again, we'll see an example of that in just a second. So let's move over to Houdini. So this is a simple file to show some of the issues that can come up with solver iterations. And I want to give a quick thank you to Thomas Lynch, I hope I said that right, who is one of our excellent alpha testers who gave us a file similar to this to highlight some of the issues he was running into testing Vellum. That really helped us sort of address these issues in the solver. So this example here, we've just got this grid. We are adding distance constraints along each edge. So we're not triangulating anything here. We're not adding any bend constraints. These just like as if we were adding, putting very, very stiff springs along each edge. And then we're pinning each side. And on those spring constraints, on those distance constraints, we're actually setting the rest length scale to 0.5. So we're shrinking down all of these springs by half. But at the same time, we have an extremely high stiffness. It's almost an infinite stiffness. So it's kind of an impossible configuration to solve because we've got infinitely stiff material that we're shrinking in half. And if we try to solve this with, I've changed a few of the settings. In particular, I've taken away any smoothing iterations. We'll see we get this not very attractive solve at all. And so what's happening here is we're getting some error because this is an impossible configuration, but because of the way we do the solve in those batches I was describing in the graph coloring, we're actually biasing that error towards the first batches that get solved. They kind of get a lower priority, and then the ones that come along later will actually kind of get a higher priority, and so they'll get solved correctly. We can actually see this if we, so we're going to take the constraint output from the, so these are actually the distance constraints themselves that we're looking at. We're taking the second output of the Vellum Solver, and we're gonna just regraph color them, and we will add a visualizer on it. So we'll look at it and we'll see that the ones that get stretched really bad are all this same color. And in fact, if we select a few of those and look at their color, it's all 0. So these are the first ones to get solved. And then these ones come along later and they basically get solved correctly. In particular, the ones that are colored 2 are going to be solved last and most correctly. So the error gets distributed unevenly. So the question is, how do we fix this? And the one way to do it is to say, well, all right, well, let's just make this no longer an impossible configuration. Let's make a much weaker springs along each edge. And now when we hit play, we will get this nice distributed, there's not really any error and everything's nice and even. The problem is that that's really not what we were looking for. We didn't want these weak springs. We wanted a very stiff, difficult to stretch material. So this isn't a great answer. So it turns out what we can do instead is increase the smoothing iterations, we can even just go to the default here of 10. And we'll see that that basically smooths out all of that error. And so what's happening here is we're solving the constraints again. We're doing another pass through the constraints, this time just doing 10 iterations. But rather than updating the point positions immediately, we're accumulating the updates that are going to be made, basically sort of the deltas, the change in point position, and then we're averaging them all together. So we're running through all the constraints, getting all of their point updates, and then averaging that together, which effectively averages out the error and smooths out the error. So it gets distributed across all the points instead of being biased towards the ones that get solved first or the constraints that get solved first. This is pretty effective. It's pretty cheap. It's only applied to distance constraints, so it doesn't have any effect on bend constraints or anything like that. So a logical question might be, well, why don't we just solve everything like that? And I should say the smoothing iterations, that's a Jacobi style solve. It was the more technical term, and the regular constraint iterations are a Gauss-Seidel, where you immediately apply position updates. And like the grain solver works with these type of iterations with Jacobi style. So why don't we just use that? And since this is only distance constraints, we can actually try that. We can switch all of our solving to just be these smoothing iterations. And when we hit play, we'll see, sure enough, we get this nice smooth geometry, but we don't really get the stiffness we're looking for at all. In fact, it turns out that this style of solving takes much longer to converge to the proper answer. So that's why we use this Gauss-Seidel or this immediate mode of solving as a default. And then we just use that kind of hybrid to smooth out any error that might come when you get impossible configurations, which happen a lot with cloth simulations, because you've always got characters that are moving their arms or in impossible ways or stretching things that shouldn't really be stretched. So when the error does occur, you want it to be smooth. So this is an even more sort of challenging setup here. On this side, we're taking our famous pig head and turning it into a sphere and then extending that out a little bit. So we've basically got, then we're turning it into cloth and setting the pig head as a collision object. And again, we're using a rest scale of 0.5, but we have extremely stiff cloth. So ideally what would happen is the cloth would stretch as much as it could over this and sort of shrink wrap the pig, but in a very sort of tight way. There's not going to be a lot of excess drapey cloth or anything like that. But if we hit play here, and this is set up with pretty much defaults, we get a not very nice solution. So we've got two problems going on here. One is that error that we were talking about before, where things aren't really distributed very nicely, as we've got, again, this sort of impossible configuration of infinitely stiff cloth or non-stretchy cloth shrunk down to sort of an impossible degree. And so the error gets biased again. So we can fix that fairly quickly by, again, going back to the defaults of 10. Let's actually just try 20 smoothing iterations in this case. And that works pretty well. So we can see, okay, now we've done a good job of smoothing out all this error, but we've still got this problem around the ears. And this is a result of the lower frequency of solving of the collision iterations. So that we were talking about before, the defaults of collision passes is 10 and constrained iterations is 100. And what that means is we're doing one collision pass for every 10 constraint iterations. So if you've got extremely stiff constraints around a collision like this, essentially the constraints are winning. So they get to update their points 10 times as often as the collisions do. So when they're fighting, they sort of get priority. And so you get this same kind of non-uniform stretching here, which is not good. It's also pretty noisy. The main way to fix that is just to increase the collision passes. And so we could also do that with more substeps. But if we're trying not to do that, let's just increase the collision passes to 50. And you'll see it slows down a little bit, not surprisingly, because it's doing more collision handling. But we get a much smoother, we still get a bit of stretching here, which is not too surprising, but we get a much smoother result right here around the ears and around the nose. And this actually starts to look pretty good. So this is a tough configuration to solve because we've, again, essentially got an infinitely stiff or almost infinitely stiff material stretched very tightly over this sort of complex collision object. So this is actually a pretty good result for just changing a couple of parameters. And actually the smoothing iterations obviously are on by default. We've increased it a little bit. And then really all we've had to do is increase the collision passes a bit more. Now that we've looked at the internals of the Vellum Solver, let's start looking at ways to control the geometry that it's solving. And one of the simplest ways of controlling that geometry is to pin it in place or to weld two pieces of geometry together. So welding, for instance, two pieces of cloth together. And in Vellum, there's really sort of two different ways to do that. There's what we could consider hard pins and welds, and then there's soft pins and stitches. And so the hard pins are geometry point attributes. So we talked about how the solver has two different pieces of data. It has the geometry data, which is the points, the particles that it's updating the positions for and velocities for. And then it has the constraint geometry, which stores all the constraint primitives. So anything that is a hard pin or weld is actually stored as a geometry point attribute. It's like a particle attribute. And when the solver sees one of those, it actually is directly updating the point position. So it's not solving constraints to move these points around. It is updating their positions directly. So there's not any ambiguity about where the point is going to end up, where its position is going to be. It is a hard specification of where that point needs to be. So if you want to create and remove these types of hard pins and welds, you actually do it by setting those particle attributes. And they're things like the weld attribute, the stopped attribute, or its mass. And in general, the only type of auto-breakable features that we have for these are for welds. So you can have welds auto-break or auto-release from one another based on things like stress. And that's actually how we do like fracturing, pre-fracturing with vellum or pre-tearing. And we'll look at some examples of that. The other way of doing pinning and stitching geometry together are with constraint primitives. And in this case, you'll actually have constraints that are solved, and that updates the point position. So these constraints are solved alongside all of the other constraints for things like cloth or hair. There will also be pin constraints or stitch constraints or glue constraints. And you have to manually create or remove those constraints, those constraint primitives, if you want to update your setup. Those types of constraints all are auto-breakable, and they also can have plasticity. So you could have things like a stitch that stretches over time based on force. And then finally, you can have those pins actually follow target geometry. And similar to the wire solver or the FEM cloth solver, you specify the target geometry at the solver level, and then you can say that a particular pin is supposed to follow that target geometry. And that's how you do animated pins. And we're going to look real quick also at how you can avoid some time dependency when working with transforming geometry. So let's move into Houdini and look at some of those concepts. Okay, so this is a basic setup that we're using to demonstrate some of the ideas of pinning in particular. So this is just a torus that we've created some, we grouped some points up here at the top and put them in a pin points group. Then we're creating cloth out of the torus, and then we're pinning that pin points group. And turning on the solver here. And if we play through this, we'll see that these are pins that are basically moving with the target geometry. So this templated geometry is the target geometry, and it's dragging the cloth along with it. And you'll see that it's a very close match where the pins are relative to the target geometry. So this is an example of a hard pin where it's updating the position of the points to directly match the target geometry. So the way that we know this is a hard constraint is we have this pin type here. So the pin type there are three options here. It's permanent, stopped, and soft. And the first two are hard constraints. And the last one is actually, the soft one is actually a constraint primitive. So these hard pins here there are two different types of them. And the permanent versus stopped generally refers to whether or not you're going to be changing the status of that pin during the simulation. And if you just want this to be a pin that's going to be there for the entire duration of the simulation, you can just set it to permanent and it will be just a fixed pin. So that's why that's the default. And then we have this match animation enabled. The orientation pin type is only relevant for hair. And it has these same settings. It can basically mirror the pin type of for the position, or it can be soft. So that's actually useful. And whenever we talk about hair, there's actually a way you could have the roots would actually be, the position would be a permanent position change or a permanent pin, whereas the orientation would be a soft constraint, which can be useful. But anyway, we're not going to look at that in this example. So we have this match animation, which tells the pins to update with the target geometry. And then the target geometry is actually specified over here. And then in the Vellum Solver, we are pointing our target actually at this external SOP over here. So if we look at what this pin Vellum Constraints is doing, if we look at some of the attributes, so what it's actually doing, this is actually, we're just looking at the pin points group here. And it's actually setting the mass of all those points to 0. And what that essentially means is it's like they have infinite mass as far as the solver is concerned. So these points can't be moved by constraints. They can only be moved by the solver. And in fact, they are moved because it has this pin to animation attribute set as well. So again, this is like the wire or the FEM cloth solver that has this pin to animation attribute. When it's set to 1, it will update the point positions to match the target point positions. If we turn this off, we'll see that basically that pin to animation attribute just goes away. And if we hit play, it'll just stay in place. So it doesn't follow it anymore. So the other type of hard pin is this stopped. And what it'll actually do is it will then set the mass similar to all the other points, but it will also set this stopped attribute. And this is useful if you're going to change the status of the pin during the solve. And that's because we don't want you to have to try to remember how to set the mass from 0 to whatever arbitrary value it is. And especially, again, if you're working with hair, there's another value called inertia that affects how it rotates, which in some ways is a function of mass. So in general, trying to set the mass at runtime is just not a very good idea. So what we have instead is this stopped attribute, which is actually part of pop. So any pop's particle can also be set to stopped of 1, and it'll actually stay in place. So we're using that same attribute here to indicate that this vellum particle should not update from constraint values or constraint solving. It doesn't really look any different if we hit play. We'll just see the cloth gets moved around and is pinned similar to with the permanent. But what we can do then is we can jump into, so this is the SOP-based version of the Vellum Solver. If I jump into this, I've got my, where I can apply forces and update the simulation. And so I've got a little very simple geometry wrangle here that says, if the frame is greater than 30, then I want to clear that stopped and that pin to animation attribute. And so if I plug that in, then after I get to the frame 30, these pins are all going to be cleared off. And then the cloth will just drop to the ground. So this is the easiest way to unpin something. If you have something that's pinned and you want it to be a hard pin, and then at some point you want it to release, you can just set stop to 0. If it's pin to animation is set, you need to make sure you set that to 0 also. You could also do things like just clear the pin to animation. So if you just want it to follow for a while and then stop following and stay in place, you can do that as well. So that's what happened there. So then looking at the other way of doing the pinning, we can do this with a soft type. And quickly, the reason you can actually set pins here in the cloth constraint as well. And that's really just a convenience, because a lot of times you want to set up cloth and then just pin like 2 points and have that be your setup. And so you don't want anything more complicated than that. But in that case, any soft pin will actually just inherit these same stretch, stiffness, and damping values. So if you want different values, you need to use a separate vellum constraint set to pin to target. And that's what we've done here. So now we've got a soft constraint, and if we hit play, we'll see that that's what we're seeing. We're actually seeing these are pins again, and it's updating the goal position of the pins, but because it's soft, it's actually got a fairly low stiffness. It's acting like a spring. If we look at the attributes that we created, they're all the stopped and pin to animation are all gone, and we're just looking at the regular mass here. So these are just regularly constrained points. They don't have any special point attributes on them at this point. We've just got new constraints. And so if we look at these, we can actually see that, excellent, sorry, just clear all these out. So we'll have all these pin type constraints here at the bottom, and here's our stiffness. And the rest vector here is the original position, and we'll actually see, actually if we do this, we can look at just the type equals pin constraints. And we'll see the rest vector is actually getting updated by the solver. So this rest vector is its goal position. So that's this value that's getting updated each time step. And if we wanted to delete those, we actually need to delete the constraint primitives themselves. So this is the Vellum constraint property. We're going to look at this in some detail in just a second. But for now, we're going to just look at this pin group. So when we created the Vellum constraints SOP and we created these pin constraints, we turned on the output group. So we actually have a group called pins here. So I actually could just type this in here as well. And it would be the same thing. These are all the ones with the type of pin. And then we're going to operate on that group of constraint primitives. And all we're doing is setting the remove, which is basically like deleting the constraints. And we're activating this stop after frame 30. So it's really doing the same thing that this unpin is doing. It's just doing it for the constraint primitives. So if we plug that in, we'll see that after frame 30, the constraints go away. And you saw that little sort of hitch when the constraints went away. That's actually that graph coloring that we were talking about. It's basically having to update that graph when the topology changes. So when those constraints go away, we actually see just a slight delay when it updates that graph coloring that we're talking about. And we can see that if we select this, that after frame 30, all these constraints are just gone. So that's the difference between hard and soft pins. The one other thing I wanted to look at real quickly is why we might set the target path this way. The other thing you can do is, so this is just a transform that animates that torus around. You can also take that transform and just put it in line here and then set it to first input. This is actually the default, and it'll work the same way. The only reason you might not want to do that is, if you notice, we've got this little green time-dependent badge on all these SOPs now. So what we've done is we put this animation up here, and then all the constraints are also time-dependent. So we're only actually reading the first input here. So this is not that expensive, but it can just, if you have a bunch of these, it can add up. So in general, it's not a bad idea to use a separate target, or if you want to do it inline and it makes sense for your setup, you can actually do the transformation here. So at this point, the time dependency is just down at this transform, and it'll work exactly the same. So it's just worth remembering for optimization purposes. It's not a bad way to do it. It's to set maybe a separate target like this, or if you can, just add the transformation down right at the bottom, right before the solver. So now we'll look at hard welds versus stitches, which are in a lot of ways similar to hard pins versus soft pins. The first is represented, the welds are represented by geometry point attributes, and the stitches are actually constraints that have to be solved. And the welds are very useful because the solver essentially treats 2 points when they're welded together as if they're the same point. So they won't collide anymore, and their positions are always updated to exactly match. So if you're trying to connect or attach 2 pieces of geometry together to make one seamless, for instance, large piece of cloth, it's a really good way to do that. And it can also be useful for tearing or fracturing effects, because the cloth will look like it's one piece before the welds get released, at which point it looks like the cloth has been tearing. So let's look at a really basic setup of that real quick. I've used the planar patch SOP here to create 2 separate pieces of cloth. And the reason it's useful is because it has these output groups here for example, this is the right seam of points here, and this is the left seam of points here, and then from this one. And then so we'll create our cloth, and then when we weld them together, we can actually specify that right and left groups for the 2 different edges here. And so what we're seeing is these purple little points represent the welded points together. And all we're doing is we're actually doing a constraint to closest point. So we're saying each point in this group should look for the closest point in this group and should set up a weld between the 2. And all that's really doing is, if we look at the output of this, if we look at the planar patch 1 right, so this is all these points, it's just setting a weld attribute. And if we look at the point numbers, so we'll look at, say, this is 98, it's just pointing at 166. And the next one down is pointing to 165. So this is how welds work, is just one point, the welded point will look at the weld target, and it'll just specify its point number there. Although actually I should say, if you have point IDs, you can use point IDs as well. And then the one other thing you're seeing, these lines here, is because we have this add bend across welds option on. And what that will do is will actually create between these triangles here that are welded together, it will create bend constraints as well that match. Because we have this copy neighboring stiffness, it'll actually inherit all of these stiffness values for bend, so that when the cloth bends, it will act like not only is it attached together by position, but it will bend like the rest of the cloth will. So if we run the solve, we've also pinned this point over here. So we'll see that the two pieces snap together, and as the sim sort of goes through, it'll start to bend, and it just bends nice and smoothly across that weld. And we're just visualizing the weld here. So if we, one thing to notice is if we undo, if we turn off our wire shading, we can see there's kind of this line here. And that's because there's still separate points. The points are actually still maintained separately by the solver. They're just updated so their point positions exactly match. So if we want to get rid of this line, if we want this to act as if it's one piece of geometry, we can use the Vellum post process there, and has this apply welds option. And if we turn that on, then what it's really doing is it's rewiring. Oh, I've actually got subdivision on too. Let's turn that off for a second. So you can see it's actually fusing those points together, rewiring those points so that there's only one point along that seam. And so then if you do something like subdivide it, sorry, you'll see you get this one nice smooth piece of cloth. If we didn't apply welds, you can see these are two separate pieces of geometry. So this is a different geometry and this is different geometry. And so when you subdivide along it, you get that seam. But if you apply welds, and we're actually going to look at exactly what that topological operation is in just a second. But just to go back to the solver, the other thing we can do with this is we can turn on braking. And we're going to visualize stretch stress. And so what we're doing is we're braking on stretch stress. And as we hit play, what we'll see is these welds release. And we're visualizing the amount of stress that is in these distance constraints that are along each one of these edges. And we can actually see in the visualization. So basically when this red makes it to the welds, so I've tied this threshold for the braking to the visualization threshold. This just references that. So when the red gets to these welds, the welds are looking at the maximum stress on all the constraints that are attached to it. So it unwelds at that point, and you can sort of see the stress kind of moves down along this line as the points are released, and we get this sort of natural looking tear. Obviously, this is kind of too straight, so we normally wouldn't do this like if we were trying to do sort of a fracturing or tearing effect, but just an example, of course. So let's turn that off for a second. And the other thing we can do, similar to what we did, and I'm sorry, we need to do one more thing. Let's keep that braking off. If we wanted to undo this manually, so not do the auto braking, but have control over when we wanted things to unweld, again, this is similar to the way we did the hard pins. So we're going to operate on the geometry and the points attributes themselves. And all we're going to do is reset them all to -1. So if we plug this in, this is essentially unwelding all of the points. So not by tearing, just doing them all at once on frame 30. So, and that's just like saying set stop to equal to 0 for a pin, for a hard pin. So it's a similar idea. So this same Vellum constraint SOP we can switch this to stitch points. And so to see the soft constraint version of attaching these points together, we can do stitch points here. And so now what we're doing is just creating constraints, little spring constraints between these same sets of points, just like a weld. But now we've got a soft constraint. So it's actually a constraint primitive that's represented along these two seams here. And again, we've actually set the stiffness fairly low, so it looks sort of like it springs. So this might be more useful for things like stitching closed a jacket or something like that, where you want something to stay in place or stay closed, but you don't necessarily want it to be fused together like one piece of cloth. And similarly to the soft constraint, if you want to remove something like this, you just use a Vellum constraint property. Again, we've created a constraint group, and we just set the remove. And it's the same sort of idea. So you'll see at frame 30, these release again. And just like with the welds, we can actually turn on braking for this as well. Let's turn this visualization back on. Although now what we're doing is we're actually specifying a braking threshold for these constraint primitives themselves, these stitch constraints along here. So you'll see again, as they turn red, as they hit that threshold, they're automatically removed by the solver. So again, you get a fairly natural looking release of the soft constraints in this case. So it's worth going into a little more detail on what's going on with welds underneath the hood, and also what's happening in this Vellum post-process SOP when we're rewiring or fusing the welded points together. This is a really simple example here. I've got 2 lines, and what we're doing is creating a weld attribute on the first point, group point 1 here, and we're just pointing it at 2. So this is as if we were going within Vellum. This is just, we're working on raw geometry here, but as if we were in Vellum, we're saying point 1 should be welded to point 2. And then we're using this SOP called rewire vertices, and we're actually rewiring that primitive that was pointing to 1. It's actually now pointing to 2. And because we've got this keep unused points on, then point 1 is still around. It's just no longer attached to any primitives. Inside the Vellum solver, when 2 points are welded together, this is actually what's going on with the constraints. The constraints are actually rewired from pointing at the welded point is actually now rewired to point at whatever it was welded to, the weld target. So if this point 1 was welded to something, it no longer has any constraints on it. All that happens is the constraints are solved as if they're attached exactly to point 2 instead, and we just update point 1's position directly at the end of the time step. That's what makes it a hard attachment. We also disable collisions between these 2 points. So then, and when we do this rewire, we actually keep a vertex attribute that tells us where the wiring was originally done, the original primitive constraints, so we can undo it. And when we undo it, it just goes back to the way it was. So this is what happens when something gets unwelded, is all the constraints that were originally on the point get restored. So that's what's going on underneath, sort of within the solver as you weld points together and unweld them together. And that's why this is a hard relationship. So basically all the constraints that were on 1 are now on 2. And so it looks like it's actually the same point. And then the geometry that comes out from a weld, as we saw, there's actually still 2 points here. It's sort of hard to see, but you can kind of tell that there are overlapping points here. There's another, it's 98 and 166. So, and this 98 actually has a weld attribute pointing to 166. So all this is doing, the Vellum post-process, this apply welds is doing another, this same rewire vertices, and it's just pointing, it's just rewiring this whole topology so that the 0.99, for example, everything that was attached to it is now attached to whatever it was welded to. In this case, we don't keep unused points. We don't want those points around anymore. We want it to be fused together like one big seamless piece of geometry, which is what it is now. So within Vellum post-process, there's one of these rewire vertices that is doing that same work. And then we could, for instance, subdivide this and it would all look like one smooth piece of geometry. Now we're going to look at a couple more production-oriented uses of welding, in particular for doing tearing effects with cloth, and using some attributes to control where and how and when the cloth is going to tear to get a lot more control over the effect. So a pretty simple setup here. We've got our pig head that we are remeshing here to get something that works a little bit better as cloth. We are pinning some areas of the cloth just so it'll stay in place. And then we're using this edge fracture SOP to split up the cloth along these, let's see, there we go, along these edges here. So I'm going to go into some detail on edge fracture in a little bit later. But for now, all we need to know is that we've effectively split up this cloth along these edges here. And we've created 2 new point groups. One are the original points that were along this seam, for instance, here. And then the other one is the new points that were created when we did this split. Then we create cloth from the geometry. We pin the points that we were talking about earlier, and then we are going to weld all of these pieces back together again. And so again, we're seeing those little purple points indicating where the welds happened and the little white lines that tell us that we have bend constraints across those welds so that this entire piece of geometry is going to act like one big piece of cloth. And then we go into the Vellum Solver. And if we hit play, what we've got here is we've got cloth pinned at these points that we were talking about. We've got a strong wind that's going in the positive X direction. And eventually this cloth is going to start tearing along those predefined lines that we created earlier. As these welds basically pass a stress threshold, they're going to unweld and make it look like the cloth tore. And if we want to look at the actual guide geometry to see what's going on here, we can see, well, so first we've got the weld breaking set. We've got a threshold set, and it's breaking from stretch stress. It's actually set to none here, but I'll show you why that is actually not really what's going on. So if we are visualizing the stretch stress here, we can see that as the stress, so that's the red parts where we've exceeded the max stress here. The red parts follow basically where the tear is happening. So we can see as everywhere it gets red, it starts to tear because that's essentially where the welds are having their so like there's a tear that's propagating along this set of welds here. And that's because the stress of the constraints that are attached to it, the stretch constraints that are attached to these welds, have exceeded that threshold. And if we turn this off, we'll also see that same fact that when you are looking at the raw geometry, you can sort of see where all these splits of the geometry actually exist. So you can actually see the fact that it's still separate geometry. But then if we run it through the Vellum Post process, that it'll actually put it back together again as one piece of geometry. And we can do things like maybe add a little bit of smoothing and subdivide, for example. Maybe a little more smoothing. Oh, actually, I'm sorry, we want loop subdivision. So we'll end up with our nice, it's a little more expensive to scrub through, but we'll see that we have one nice, piece of geometry that gets torn over time. So the way that we are controlling this is with attributes. So if we look again at, because these are hard attachments, these are hard welds, the new points group, the one that was created by edge fracture, is the one that's being welded. And we can look at the attributes that are being created. And essentially it's our break threshold here, our break type, which is currently set to none. And we're looking at the weld. So all of these points are being welded to some other point within the simulation. And as we scrub through this, actually we want to be looking at this one, sorry. We'll see that at some point the break type changes to stretch stress, and this is when these fracturing starts, or the tearing starts happening. And over time, we'll see the welds are automatically being set to -1. So this is when the solver is seeing that the constraints attached to them have exceeded the threshold, and they're being released by setting the weld to -1. So the solver is doing this automatically. And so all the -1s have been unwelded because of stretch stress. And if we go dive inside the solver, again, this is the SOP version, this enable break unwelding, this is what's setting that break type after 20 frames to stretch stress. So that's how we're making it so that it doesn't start fracturing until 20 frames in. And then we can control this a few more ways. We can do things like, let's create an attribute that is only positive for all the points that are in the positive x-axis. So all the points that have, actually let's turn this on, and we're actually going to create a visualizer for this. So we created this break threshold scale attribute. Turn on the visualizer. And what we've done is we've set -1 to all the negative x point values, and we've set 0.5 to all the positive x point values. And then in our weld, here, we can scale by attribute, and we're scaling by the break threshold scale. I already had this set, but because the attribute didn't exist, it was just treated as 1. But so now we're actually scaling the break threshold by that attribute. We can see that here. We've got some that are negative, and we've got some that are scaled by 0.5. And the negative ones, a negative break threshold basically means never break. Never. So a weld that has a negative break threshold will never release, and the rest of them are scaled lower. So if we solve this one, we'll find that, again, after the first 20 frames, we'll start to see that same tearing, but it'll happen a little easier because of the lower break threshold, but it'll only happen in the points that were originally in the positive x-axis. So obviously you could paint this on, or you can generate it by noise, or there's all sorts of ways you can set that break threshold scale so that you can control exactly where you want that that tearing to occur. And then if we wanted even more control, we could do something like turn the braking off altogether, and then go over here. And so we're going to take that original geometry and let's create a group that we're going to call unweld. That's just an expanding bounding box here. It's just animated and grouping. And and the idea is it's going to set all of these points into the unweld group. You could also do this by color. There's sort of a lot of ways you could do this. And then within the Vellum Solver, what we're going to do is actually, we don't need this anymore. We're going to bind one of our inputs to that grouped SOP, and then we're just going to look up the point number there, and if it's in that group, we're going to unweld it, and do that manually. So this just gives us a lot more control over exactly when that welding happens. So again, you can see as the points, as the group is sort of moving across this way, we're unwelding all of those, all of these points. So you can see it's actually, we don't need this visualizer anymore. So it's just all coming apart. And then we can do things like maybe add some noise and don't unweld some of the points based on that noise, and it'll do a sort of similar effect. But now there will actually be a few points that never get unwelded, and so you'll sort of get that same effect, but then some points will stay permanently together. So it mostly tears, but not all the way. Again, it's probably best to look at this from through the post process, so you can see the effect of applying the weld, or applying those welds, so it looks like one piece of geometry. And still got this subdivided. So that's just some ways to control how welding occurs or unwelding occurs for tearing effects. And we're actually looking at a slightly more complicated example now. So this example shows how you might do something like a popping balloon. So you've probably seen lots of Vellum demos where they show things inflating or objects inflating. But this is an example of how you might solve or simulate a balloon that pops, or any kind of inflatable object that pops. And we're going to sort of fake a couple effects here, but just the whole workflow shows a couple of kind of interesting aspects of welding and unwelding in particular. So we're just creating a sphere here. This is probably, it's a meter radius, so it's really more like a big beach ball that is going to pop. And we're doing the same thing where we create a attribute noise for the break scale. So we're going to scale our welding or unwelding by an attribute again. We're doing an edge fracture again. And in this case, all we're actually turning off the sort of auto creation of pieces, and we're just drawing a simple little curve. So we've drawn a simple curve here that's going to actually be where we want to break this geometry. Although again, we're going to break it along the edge. We create cloth. We're adding a pressure constraint, which is what it makes it act like a balloon. And then we're doing the weld. So again, if we look at the weld, we're seeing we've got all these points that are running along that fracture that we've created, or that edge break we've created. And we've got the little white lines telling us we've got bend constraints along it. So again, we're just creating a sort of inflatable balloon that has been welded back together again. If we hit play on this, what's happening in the simulation is the pressure constraint is actually being inflated. We're increasing the rest volume so that it's causing more and more stress on the cloth. And then eventually those welds are breaking because of that. And then it's sort of flying across the room as the air escapes from the balloon. So let's look at how we do something like this. So this is actually the post process. So I think we're applying the welds and we're doing a subdivision on it. So that's why we get this nice smooth one piece of geometry. And so you can actually see the fractures occurring here right along this line as the stress along it gets too high. So, and if we look at it within the DOP-net, so this is actually a DOP-net setup, and we're viewing the stress. So the reason it's getting more and more stress because we're inflating the pressure constraint, and then eventually those welds start to break. And then if we actually create this, we're going to add this visualizer. We'll see we get these vectors that are showing us kind of where we need to apply an impulse to make it look like the air escaping the balloon is sort of shooting it across the scene. So now I'm going to sort of start over and show a couple of turn off a couple of these effects so that we can kind of start from the beginning. First, we have this inflate. So this is the Vellum constraint property. We're going to go into a fair bit of detail on this, but all we're doing here is on the pressure constraint group, which is just the one that makes it inflate. We are animating up the rest length scale. So that's basically how you inflate a balloon over time, is you just increase the rest length. And as it expands, it's going to create more and more stretch pressure or stretch stress on the cloth that is holding the surface together. And then we've got this sort of complicated Vex expression here. So let's remove a couple of things or disable a couple of things. We're going to turn that remove off. And so now all we've got is so I've left the inflatable rest length on and nothing else. So what we're going to see is it's going to inflate and the welds are going to break, but it's really kind of strange what's happening here. We've got this kind of weird effect where the balloon is just kind of like moving around and it's still sort of staying around the same size. And that's because the pressure constraint here is actually still active. So what it's doing is it's still computing the volume of this object, and it's trying to maintain that volume by expanding the cloth outwards to keep that volume. But because it's not a closed surface anymore, we're getting sort of a very weird estimate for what the volume of the object is, and we're just getting this kind of really strange look. So what we first need to do is figure out, when do we remove the pressure constraint, because the pressure constraint, when it removes, is going to make it look like the balloon deflated. With something like this, you could probably just keyframe it, but we're going to try to be a little bit more procedural here. So what we've actually done here is we're going to turn this remove back on, and we've turned on use Vexpression. So we're going to use an expression to figure out when we're going to remove that pressure constraint. So what we're doing here is we're actually looking at so again, we've bound the one of these inputs to the first context geometry, which is the original geometry, right, coming in here. And then input 2 is actually the points, the DOP data. This is that geometry. So this is the particles, essentially. So what we're going to want to do is compare the number of welds that are in the current simulation geometry compared to the original geometry. And when that goes past a particular ratio, we want to say, okay, well, enough welds have been removed that we want to basically pop the balloon. So that's what this is doing. We're basically saying expand point group. So find all of the points where the weld is set. And that's how many we have originally in the geometry. And then we're going to compare it to the current geometry, how many welds are existing. And as soon as half of them are gone, we're going to remove the pressure constraint. So we're going to pop the balloon. So now when we hit play on this, we'll see the same thing. The balloon is going to start to inflate as we scale up the pressure rest length. But now when the welds remove and half of them are gone, we're going to essentially deflate. So we remove the pressure constraint and the balloon pops. And again, subdivided, this generally looks better. So that's nice, but we would like to also simulate the air or emulate the air that's coming out of the balloon that's going to sort of shoot it across the seam. So that's what this does. So we now have a geometry wrangle. So again, we're running on the geometry, meaning the points of the particles, essentially, of the simulation. And we plug this in. This is the reason we're using a DOP-net here, is we have to do this in the third input, this post-solve input. So when a weld is broken, it's actually put into a broken point group. the point that is unwelded will be in a broken point group, and you can actually operate on that in any of these geometry wrangles here. The same thing actually happens for constraint primitives. So you could actually operate on the constraint primitives at the same time. They're put into a broken primitive group. But for now, we're looking at unwelded points, so it'll be in a broken point group. So what we're going to do is we're going to look at all the unwelded points. So every weld that popped, basically, or that broke in this particular time step. And we're going to look at its pressure gradient. So its pressure gradient is, you can think of it as essentially the normal, but it's really the direction that the cloth has to expand outward, or the point has to expand outward to increase the volume the most. And it looks a lot like the normal. So what we're doing is we're taking the opposite of that, the inverse of that, we're scaling it up and adding that as an air vector to every point. And then in our pop wind here, we're actually turning that air vector into wind. And this works well because we've got this tangent and normal drag set here, which is what makes cloth behave as if it had sort of a lift force on it. So where the cloth is normal to the wind, it will get a big effect, and where it's tangent to the wind, the wind will sort of slide right by, which is generally what we want to have happen. So what we're doing is we're applying that air as a wind force, and it'll automatically take into account whether or not the cloth is aligned against or alongside that air. If you notice, this is actually going to be doing the exact same thing for every point that's on this geometry. If we had a bunch of balloons that were popping, we'd have to do something like look for only the welds that were a part of the same balloon or something like that. So we're not doing that here because this is kind of a simplified example. But so what it's doing, looking at all the broken welds, if there is one, it's adding its inverse pressure gradient to the air vector. And that's what's basically giving those sort of little wind impulses to blow it across the scene. I wanted to finish up this section on welding by talking about edge fracture, which is a new tool in Houdini 17 for splitting up geometry along existing edges. And this can be really useful for then welding back together again to do like tearing effects like we've seen. So the reason you want to tear along existing or cut along existing edges is because, let's say we've got this nicely remeshed pig head here, and so we've got generally really nicely sized triangles. It's fairly uniform across the geometry, which is really good for cloth simulation. But if we use something like Voronoi fracture, and this is I've got the interior surfaces turned off, so it's really just splitting up the surface of the mesh here. We'll see that we get this straight line that's actually cutting all of these triangles into these tiny little slivers. And so if you see like right here, you get these tiny little slivers here, which is not very good for cloth simulation. And not only that, it also means that all of our tears would be perfectly straight, which is also not very realistic because usually the tear is going to kind of meander along as a material tears apart under stress. So for that reason, we wanted a way to take input geometry and tear it or cut it up, but again, only along existing edges. So this takes and borrows an idea from the game div tool set actually. And what it does is it actually poly reduces. So it reduces the input mesh to generate a bunch of low resolution edges. And then it uses the find shortest path SOP to trace the edges between each pair of points here, and then creates a group from that and cuts along this group. So it's the find shortest path that's letting us basically cut between or trace along these edges between these two points, for example. So all we need to do for edge fracture is really provide lines that are going to give us the cuts we want. So it has this initial pieces option here, which is just really specifying how many polygons to poly reduce the initial mesh to. And that is a rough count of how many pieces we're going to have. So we can have just a few. We get these very large pieces, or we can go pretty high up, and we'll get lots and lots of small pieces. So again, and we're just seeing the poly reduction as the guide geometry here. So on top of the initial pieces, you can also, because we're just drawing lines or just providing input lines, we can actually draw our own curves. So I'm just hitting enter here, and I can then start tracing curves along the geometry. And this way we can actually sort of guide where exactly we want the cuts to happen. And it's not going to be exact because, again, it's tracing along the edges that are close to the curves that we've drawn. And then the other thing worth noting is that you don't have to actually draw an entire piece here. We could just sort of, let's say we just want the piece here to possibly tear across like in the middle, but it shouldn't have to be in its own entire separate piece. If we look at the result of turning that into cloth and welding that, we'll see that we've got this weld along here. So this could tear open, but it wouldn't tear this piece into an entirely new piece. We're not cutting it. We're not cutting it in half, for example. We're just making a tear along the middle of it. So that's something that draw curve lets you do that won't happen with the initial pieces, which always cuts into separate pieces that are distinct from each other. If we want even more control, we can turn off that initial pieces option and do the polyreduce ourselves. And this provides these edges that we were talking about. And then we can, for example, dissolve some of them. Like if we want the head for the most part to just have one big piece, we could dissolve those edges there and then fracture with those, and we'll see this one big piece is here. And then we can send that in to draw a curve and then further draw on top of that if we wanted to. So this gives you a lot of, as long as you provide sort of interesting curves, it will trace them in ways that can then be used for fairly realistic looking tearing. Just to take this one step further, we can do something like that Voronoi fracture I showed before. But then we're going to actually take that and get just the edges. So these are now just the edges of the Voronoi fracture on the surface. And we're going to remove all the points that aren't at junctions and convert that to a bunch of lines, and then use that as our input to edge fracture. So what we're sort of getting is a edge following Voronoi fracture. So you can see as we go up and change the number of points, we're getting sort of the same Voronoi fracture type pattern, but then following all the edges, which can be useful because we've got different ways of everybody's, sort of accustomed to controlling Voronoi fracture in various ways. You can scatter points in particular areas, for example, if you want to fracture there. So being able to go from Voronoi fracture to this edge fracture is kind of interesting. And what you'll see is this, you can see sort of another example of what happens if you have if you don't resample the edges, basically. So if we look at this here, we've taken away all the non-junction points. If we add them back in, what's happening is we've got all these edges actually that are going to trace exactly along this straight line. So when we convert to line, we've got all these points that we're going to send into find shortest path. So the paths that are going to be found are going to actually very, very closely mirror the inputs, which is going to actually make them fairly jaggy. You can see that here. So you can see the difference if we turn that off. You get this kind of more natural sort of meandering look. And then if you keep the non-junction points in there, it's going to very closely try to follow this line, which gives you sort of this jaggedy look, which might be what you want. It might be interesting. So anyway, there's just a few different ways to create sort of interesting patterns for using edge fracture, which can then be sent into welding inside Vellum to get some nice tearing effects. Let's look now at animating constraint properties during a simulation. And you usually do this with the Vellum constraint property DOP. And this could be for things like changing the stiffness of a constraint or its rest length or something like that over time during the simulation. So possibly as a result of some action that happened in the simulation. And this is generally analogous to the POP property DOP. If you have worked in POPs at all, you might have run into this, but it's the same idea where you've got a bunch of toggles that turn on which attribute or which property you want to be changing. And then there's also a use the expression option, which lets you actually write little vex snippets to further control how you want to change those properties. Very often you're going to operate on specific primitive groups, constraint primitive groups. So if you create, say, a bunch of attached to geometry primitives, you might toggle on that output group option and call it attach or something. And then you'll actually update just those particular constraints from within DOPs with a particular Vellum constraint property. Doing it this way avoids changing the topology or redoing any graph coloring if all you're doing is updating attributes. So we've looked at how Vellum will partition up the constraint primitives into these very fast batches it can send off to the GPU, and we don't want to be redoing that or re-importing all of that constraint geometry just to update, say, stiffness or something like that. So we want something much more atomic than that. So when you update just a single attribute on these existing primitives, the way that Houdini works and the way that it works with OpenCL, it will actually only send that changed attribute back to the GPU, but it won't touch all the other attributes, and it won't change any of the graph coloring or any of these fast independent sets that we've generated before. So it's fairly quick. It's actually quite quick if all you're doing is updating a single attribute. The Vellum constraint property DOP gives you access to both the constraint geometry, so those constraint primitives we've discussed, as well as the geometry data, which is the particles. You can add additional inputs as well if you want to bind to, say, an external SOP to look up some animated values or noise values or something like that. There are also pseudo properties for remove and broken. So, and we've seen some of these examples before, but remove will actually just remove the specified constraint, and broken is used with the auto breaking capabilities of Vellum to essentially allow you to override a breaking event. So it will let you do something like if you wanted to, for instance, change the stiffness to very low instead of actually breaking, you can do something like that. The other way of animating rest state is to use the Vellum rest blend SOP and DOP, and we'll see examples of both. And this will only let you animate rest lengths. So it's not going to let you do stiffness or damping or anything like that, but it's in some ways can be a really easy way to update that state because you can just point it at external geometry. So it can be animated geometry that's bending or deforming, and you can actually match the rest state of the constraints to match that. So it's actually an interesting way to provide some animation to during a simulation, but by animating the external geometry in its original rest state. And so we'll look at some examples of that. The original wire solver and the FEM cloth solver in Houdini both have similar capabilities. So we'll look at how you can do that in Vellum. So let's move into Houdini and see some examples. So we use this simple setup to demonstrate animating constraint properties during the simulation. We've just got a simple grid here that's sitting on the ground plane. We're creating a group, a regular group of points that we're doing by just selecting every 11th one of them. Then we're creating cloth from that and attaching those irregular points to just a copy of the grid transformed up by a meter. So very simple. Oh, and then we're also, this is the attached to geometry. We've got these not very high stiffness, so these are going to act like springs, fairly high damping ratio, and we're setting an output group called attach. So we're going to be able to update this by using Vellum constraint property by referencing the attach group. So if we hit play on this, nothing really interesting is going to happen because we've specified a bunch of constraints and they're already at their rest length. So to solve them, the solver doesn't have to do anything. Let's say we wanted the cloth to actually rest at about half a meter up from the ground plane. We could go in and change the rest length scale of these constraints to say 0.5. And now when we hit play, it moves up to about half a meter above. And it actually does it fairly smoothly, and that's because of this high damping ratio. So the constraints can't react that quickly because they're highly damped. But if we go back to the default damping ratio, which is pretty bouncy, we'll see that they kind of fly up really quickly and they sort of start to intercollide or self-collide, and it's just a little sort of extreme. So let's say we wanted to animate this rest length scale from 1 to 0.5, and you might initially think, well, I'll just set a keyframe here. And then I'll go to frame 24 and I'll set another keyframe and I'll hit play and nothing happens. And that's because, as we discussed, the solver really only looks at these constraints at the beginning of the solve, or imports the constraints at the beginning of the solve. That means that any changes to the attributes that are done at the SOP level they're not gonna make their way into the solver. So if you want to animate them, you need to do it from within the simulation itself. So let's get rid of that and set that back to the damping ratio back to 0.1. So we've looked at this before, but the other thing to remember is that all we're doing when we set these various these various properties here, or parameters here, is we're setting attributes on the constraint primitives themselves. So they've got things like stiffness and a constraint type. We're just looking at the attached group here. Rest length and damping ratio. So we're just changing those primitive attribute values. What's nice is, of course, we've got lots and lots of ways to change attribute values. We can do it in Vex, we can do it with attribute randomize, or there's all sorts of ways to do it. As a quick aside, if you're worried about seeing all these duplicate values and duplicate strings, the way Houdini represents strings internally, string attributes, is it actually just stores offsets into a unique string table. So these will actually be all storing the same value. And then on top of that, Houdini uses a paged data structure where it can collapse common values or a sequence of common values down to a single value. So you get a fair bit of compression going on when you store things like this. So it takes up a lot less data than you might initially think. But so as you can see, when we're changing the rest length scale, all we're doing is changing this attribute value over here. So if we want to do something like randomize those values, we can use an attribute randomize set to just operate on the attached group primitives and multiply the rest length by a random value. And if we hit play, we'll see we get that same sort of effect, but now all the rest lengths are sort of randomized within this kind of range that we specified. But again, it's not animated. So let's look at how we might animate that, use those random values and animate them. So if we go in this again, using the SOP version of the Vellum Solver, so we'll just dive into this, and we've got this Vellum constraint property set here. We're operating on the attached group. And for now, let's start off. And if all we do is disable it and hit play, then again, nothing really changes. We haven't really done anything here. Because this rest length scale is enabled here, this means that if any value we type here will actually update the attached constraint rest lengths. So, and in this case, because we're operating within the solver, we actually can animate this. So we can set that to 1, and then we can go to 24. We can set this to 0.5 and set another keyframe. And when we hit play, you'll see now it's actually animated. And this is again because we're within the simulation. So this is just an easy way to animate any of these properties that you want to use. But if we want to have a little more control than that, we can use this use of expression thing here. So I've got just a little one that I've written here. And so what we've done is we're just choosing a random number based on the primitive number. So we can access things like primnum because we're just in Vex operating over primitives. So we are doing essentially what that attribute randomize did before. We're choosing a random number between 0.25 and 0.65. And then we've got this amount that we're getting from the parameter here, which is again just animated from 0 to 1. And then we're just fitting from 1 to whatever our random scale is. So this is just doing the same thing of animating, but instead of animating to a particular value, it's animating to whatever this random value is. And then we've got this, we'll look at this in a second, but this actually sets that remove value as well. Because this is not enabled, it will actually be ignored. So if we hit play here, all we're going to get is a nice smooth transition to that randomized rest length value. And then if we enable the remove, then it will start actually looking at the value of this and removing any constraints. So in this case, we're basically just coming up with a random number based on the constraint number and the current time. And if it's less than the threshold, which is a very low threshold, then the constraint will actually get deleted. So this is really just going to be sort of randomly removing constraints over time. And you can see it gets a little more active in the simulation because we are just randomly letting go of pieces of the cloth as the simulation progresses. And you can see as we go further along, we're losing more and more constraints. And if we play it through all the way, which I don't know if we'll do, we end up losing basically all the constraints. So that's a pretty basic example of doing things. You can animate stiffness, basically pretty much all the different values, breaking and plasticity and all these sorts of things you can animate by using this Vellum constraint property dot. And the bindings that we talked about is operating on the constraint geometry. So it's operating on the constraint primitives. And the second input will actually be the geometry. So it will be the particles themselves. And we'll look at an example of using that now. We looked before at how some of these values in Vellum constraint SOP can actually be scaled by attributes, but not all of them can. And if these attributes are changing, then this doesn't really work also, because this is, again, like we said, this is to set up the initial state. So let's look at how, let's say I take this initial grid and I want to add some noise to it. This is just using attribute noise, and we're going to create this amount attribute. And let's create a visualizer for that. And so all this is doing is doing animated noise between 0 and 1. So let's say instead of having just an animated single parameter for that amount between 0 to 1, we actually want to look up this animated value for this animated point value and use that instead. So this is going through to this amount null here. So if we go into this other Vellum constraint property, this is similar to what we had before as far as setting rest length scale, but we've added an input here. So we've added a reference to that that amount null, and it's going to be the third input. And so what that's going to let us do is actually update these rest length scales based on this and those animated values. And so what we're going to do here is have this expression which does the same thing. It generates a random number. And then we're looking at, so because we're operating on these constraints, we can look at which of these points is being affected by this constraint. So we can do that by just looking up the prim points array and grabbing the first one. So all of these constraints are only going to reference one point. So we can grab which point it's going to be and then go look up that point number in the third input, which is that attach input. So instead of using just this simple 0 to 1 parameter, we're going to actually use a different value for each point. It's actually an animated value. So we're looking up that amount. We're just using this point expression to go grab that the current value of that amount, and then we're doing that same fitting of the rest scale between 1 and that random value. And if we use this instead, then what we'll see is we actually get an animated set of rest scales. And so let's actually let's go back and so what we're doing here is we're just doing an attribute copy, and it's just so we can visualize it. So we're copying the amount variable onto our simulated cloth, and that's just so we can simulate it. So just so we can visualize it. So you can see where it's red, that's close to 1. So it's doing the rest length scale near its random value, and if it's 0, it's back to the original. It's close to 1. So we can see this animate over time. And obviously you could paint this, you could sort of do it however you want. And actually, let's look at an example of painting it. So if we go over here, I've created this attribute again, and just painted a real simple little shape here. And then we're actually using a blend shape. And this blend shape is going to just sort of blend in the value of that amount over time. And so if we use that for our amount source instead of the noise, then what we'll get is this sort of blend into the rest lengths everywhere it's painted. So again, just a sort of simple way to go from the constraints, we're going to look up which point is affected by the constraint, and then going and looking up some value, and it could be anything really, from some external geometry that's animated, and then using that to animate some properties of the constraints. So lots and lots of things are possible with workflows like this. So another way to update constraint properties is by using the Vellum rest blend SOP and DOP. And so when using it in SOPs, it's just sort of another way to set the rest lengths of the constraints. Using it in DOPs, you can actually use it to animate those rest lengths and change the state of the constraints over time to match some external geometry. So this example shows a couple of different ways of doing that. So we've just got a torus that we have flattened, made sort of into a little pancake, and then we've got an animated blend shape over here that's going to give us some rest geometry, what we're calling rest geometry. So all it does, you can see over time, it just sort of goes back to its original shape. And we're creating cloth from the flattened version of it and sending it into the Vellum Solver. And what's going to happen here is we've actually set up this Vellum rest blend DOP. So we're affecting the bend and stretch constraints. So those are the two types of constraints set up by the Vellum configure cloth tool. And the source for our rest geometry is actually going to be that external SOP that we just looked at. And we're just going to blend into that. And we're going to do it every frame. And what that means is that we're going to start off with the geometry and all the constraints thinking that they should be flat. And then over time, we're going to blend to this version, this sort of fat version. So the constraint rest lengths are all going to update so that now they actually match this instead. And what that will look like is as if we sort of inflated. So we've got the rest templated here. You can see that as we change the shape of it in rest space, so we're just transforming it in rest space, but it affects the simulation because it's updating the constraint rest, the constraint properties to, or the constraint rest lengths to match this animated geometry that we've got here. So there's lots of sort of interesting effects you can do with this. You can also affect how fast you want to blend into the rest version versus the current version. If you set this to something low, you'll still eventually blend to that inflated version. It'll just react slower. So that's what we're kind of seeing there, is it sort of gets there eventually, but it just takes longer for it to blend into that expanded rest state. So the Vellum Rest Blend DOP is actually using the Vellum Rest Blend SOP internally. So the SOP version, so here we've got an example where we've used Vellum Drape. So Vellum Drape basically is for sort of draping geometry over, draping cloth over usually initial collision geometry, so that you want to basically start the simulation from a pre-draped state. So that's all we're doing here is draping 80 frames worth of this same simulation. But then what we're doing in this SOP is we're actually saying we want to use the current state here as we want to update the rest lengths of all of the constraints to actually match this. So instead of being flat, it's going to have this bend kind of baked into it. And then we've got a pin to target here constraint, which is going to match this target, which is all this does is transform up over time. So we're just going to basically lift this up so we can demonstrate that it's got the bend baked into it. So that's what we're seeing, is this bend here is that has been updated, or the constraints have been updated to have that bend kind of baked into it using this Vellum Rest Blend. If we disable this, then when we lift it up, you'll see it sort of just goes back to its original flat version. And you can do the same sort of thing using external geometry. So in this case, it's actually just blending from this draped version back to the original torus. And so that all that looks like is it's just sort of going from draped to back to sort of original fat torus. One thing you might notice is we've actually set this only to 0.75. So it's actually not getting as big as the rest geometry because we're not blending all the way up to it. So that's how it works for sort of simple geometry. I wanted to show one other example of Vellum Rest Blend because it shows how to use this when you're working with multiple pieces of geometry. So this is a slightly more complicated example of Vellum Rest Blend. And in this case, we're actually using multiple different pieces of geometry, and then we're going into a DOP net that's going to use the Vellum source DOP to actually bring in these different pieces of geometry. And in fact, in the case of the tori here, we're going to actually sort of emit them over time. So if we look at what we've got here, the most basic is we've just got a piece of cloth that's just going to fall down, very simple. And then on top of that, we're adding this these tori that are being emitted every 20 frames. And they've got a rest shape that is both bending and it's now you've seen it sort of inflating as well. So it's going to be following that rest shape. And then we've got one more thing that's coming in, and that's, so let's get rid of the cloth as well. These are these L system trees. And what they're going to do, these are actually hair, this is branching hair, which we're going to talk about in another masterclass. But, and so what these do is they actually will, for a while, they're going to blend to a sort of a twisted version of the geometry, and then after frame 72, they're going to go back to the original geometry. So that's why they sort of look like they get released, or sort of they go back to their original state. So all we've done here is we've got something very similar for the rest shapes for the tori here. You can just see they sort of bend and then they inflate after a little while, and the trees just twist. That's this one, and the original one is what we originally sent in, the original untwisted tree. So the main point here is just that when we enable all these, Vellum source, just like the emitters like pop source or pop location, actually create streams. So there's actually pop streams that are created for this geometry, for the particles that make up, for instance, the tori here. So if you want to have like a pop wind or something that only affects the tori, you can just put it right here and it will only affect them. Vellum rest blend for this group here, when this is unchecked, it actually looks up any streams up above it. So these, essentially the Vellum rest blend will respect these streams. So the geometry for everything that's coming in for the torus should only be rest geometry for the for them, and for the trees the same way. And what that also means is that you need to make sure that, so after the first frame, I've only got one of these things, and after, say, the 21st frame, we're going to have two of these tori. And so we need to make sure that in the rest geometry, there's the same number of points here as we have in the simulation. So because we know we are emitting every 20 frames, if we go to the rest tori, that's actually what this copy does, is it's making sure that, well, at this point, okay, we've got two. So it's not moving them around, it's just making sure there's the same number of points, because it looks it up by point number. So that's how you set something up that's got, this is kind of a complicated or more involved setup. I'm not sure how often you actually need multiple pieces of rest geometry deforming like this, but in case you do, and you need to source it like that, you should remember that Vellum rest blend will respect the emission streams, and that you need to make sure that the rest geometry has the same number of points as the simulation geometry. And when you do it, you can get these interesting animated effects that sort of just from having animation in the rest geometry itself. So that is how you can animate constraint properties. Let's move on to dynamic constraints in Vellum, which are typically constraints created during the simulation, often because two pieces of geometry may be moved close to each other or pulled away from each other or something, and you want to add constraints based on things like proximity. Typically, you'll create these with the Vellum constraints DOP. This is very similar to, or at least in terms of parameters, to the SOP version, because it internally uses the SOP. There are a few things that are disabled, but for the most part, you can copy any parameters over from the SOP to the DOP and get similar results. In general, you're going to want to create an output group for the created primitives, the constraint primitives, and also leave the keep unique within group option on. And this is because if you're, for instance, stitching a point on a piece of geometry to another piece of geometry, you don't want that point to be constrained a huge number of times. You typically are going to want it to just have one particular constraint created on it, not a ton of them. We'll see some examples of that and some exceptions to that, in particular for glue. But typically that's going to be on. It's on by default. Some of the dynamic constraint types that you'll be creating with the Vellum constraint DOP are things like stitching geometry together, gluing geometry together, attaching Vellum geometry to external geometry, and pinning geometry in place. We'll look at examples of all those things. And sometimes if you're using the Vellum sources workflow, so you've got several different sources of Vellum geometry and you're bringing it into DOPs, into a DOP net from separate Vellum sources, then the only way to really apply constraints to those is after the fact within the DOP net itself. And so again, we'll look at an example of that. So then in that case, it's not really a dynamic constraint in that you're not creating it as a result of some situation inside the simulation. You're just doing it to set up the simulation, but because of the way you've specified the geometry, you need to do it from within DOPs. With the dynamic constraints, it's particularly things like stitch and glue and attach to geometry. If you use them in concert with braking and max distance, you get sort of sticky collision effects. So you'll get constraints that only get created when objects or geometries are close to each other. And so then they'll sort of hold the geometry together, but then once the stress builds up, they'll break, and it makes this kind of sticky collision. And we'll see some examples of that. All that you're really doing with this workflow is creating new constraint primitives in that constraint geometry data like we've been talking about. So in theory, you could actually do the exact same thing just with a custom geometry wrangle. And so I'll show an example of doing that. You don't necessarily need to do that, but it's just sort of something that if you want some very specific, very custom way of creating constraints, it is possible. And finally, we'll look at how you can remove geometry from the simulation. And this is just a little trickier than it might be otherwise, because we do have the situation that if you need to keep the point counts or the point numbers in agreement between the geometry data and the constraint geometry data. So we'll look at how you do that if you want to remove points from the simulation. So the first type of dynamic constraints we're going to look at are attached to geometry constraints. These are a pretty simple way to have vellum geometry attached to geometry that is often the collision geometry. So this is really useful for the sticky collisions that we were talking about. As the collision geometry moves closer to the vellum geometry, the constraints will be created, and then they can end up like breaking because of stress and that sort of thing. So all we've got here is some vellum hair that is hanging down here. It's pinned at the top. And this sphere here is both our collision geometry, but it's also going to be the target for our attached to geometry constraints. And if we play this, we'll see as it moves into the hair, these constraints get created, and then you can also see them breaking over time as they turn red. Here you can see the stress gets strong enough that they are going to break, and then they'll sort of snap off. And you can see the points, then even the points that have broken, once they've broken, they can actually reattach later to the same piece of geometry. So the way this is set up, it's pretty simple. This vellum constraints DOP here looks, for the most part, just like the vellum constraints SOP. We have this activation, so just whether we want it to be on or not, and then how often to create constraints. And so this can be either only on creation frames. So this is more useful when you're, for instance, having multiple vellum source things that you want to constrain together. But if you want to do dynamic, you usually want either each frame or each substep. And this is really just for performance reasons. If you've got a bunch of substeps, but you only really care about creating constraints on each frame, you can use a lower frequency just in case the constraint creation is expensive. It also has to do, because we're changing the topology by adding new constraints, we have to redo the graph coloring that we talked about. So it can be a little expensive to do it every single substep if you've got a bunch of substeps. I think we only have 2 in this case, so it's not that much of a difference. But then we have the constraint type, and we're constraining all the primitives. So any vellum geometry points can be constrained by this one. And then the target path is actually, we're just borrowing it from the static object here. So from this collision object. So all that's doing is saying we want to constrain to the same thing that we're using for collisions. And that's why we get these sort of sticky collisions. The other important part of that is max distance. So we only want to create the constraints once the vellum points get close enough to that object, to that target path object. We want to both constrain to the closest point on the primitive, on the target geometry, and use the closest location. So we're not actually restricted to constraining to points on the geometry. We're going to points on like in the middle of the primitive here, for example. And then finally, so we've got sort of a not very stiff springs type constraint with a reasonable damping ratio. And then we're creating this output group, as we talked about, and doing the keep unique within output group. So what that means is, like, say when one of these points here gets constrained by this DOP, it stays constrained, and it's only constrained that one time until once the constraint breaks, it can then actually start being constrained again. So that just means that instead of you won't have this particular point trying to constrain itself over and over and over again, which is really generally not what we want to do. So And then and then we also have the breaking threshold on. So that's what gives us the constraints that are going to break over time as the stress builds up and give us these kind of sticky collisions. So then the other interesting thing I wanted to show with this, just because I mentioned it earlier, is we can use this Vellum constraint property and look at the broken group of constraint primitives and change their stiffness to 10 and then override the broken. So when we're using this expression that basically says if the z-axis point position is greater than 0, then it can still be broken. Otherwise, we're overriding it. And so if we turn this on, what this will do is it'll mean that all the constraints over here that normally would break, they're just going to turn into very low stiffness constraints instead. You can see that happening here. So that's why all these ones just turn into very low stiffness constraints instead of breaking. So we're overriding the breaking and changing the stiffness to something very low. And that's also why they're stretching so much. So that's just can be kind of a useful effect. So that's kind of the most basic approach to, well, actually, let's just show this real quick. This works as well with cloth. Not that there's too much difference here. So just showing that the hair and cloth pretty much work the same way for these types of constraints. What we're doing in this SOP level is we're actually using the Vellum pack SOPs to turn both the geometry and the constraint geometry into one piece of pack geometry. And then that's mainly just so we can use one switch to switch between the two setups here. And then we just use an unpack to get back to our geometry and constraints separately and send it into the DOPNet. And so this is a very similar setup in a different file but in this case, instead of attaching Vellum geometry to external geometry, we're stitching or gluing Vellum geometry together. And so in this case, we are actually stitching the cloth to the Vellum hair here. And again, we just set them up to be breakable. So you get this kind of sticky colliding effect again. In this case, obviously with self collisions. And we're just visualizing the stress so we can see as they turn red, that's basically when they start to break. So the only real difference here is we've set this up to, again, be on each frame, but now we're doing stitch point constraints, so we're actually stitching between two Vellum points. So that's what these constraints are always going to be, between a point on this geometry and a point on this geometry. And we are going from the cloth to the hair group. And that's generally how, just for what it's worth, if you're ever, especially if you're welding, you generally want to go to hair, because hair has an orient attribute that the cloth doesn't. So in general, if you have hair geometry and non-hair geometry, the target should usually be the hair. And we set this up to have a max distance again. So these only get created as they get close to each other. And again, a sort of a weak spring type constraint. And the same thing with an output group and breaking threshold. So this is very similar to the previous setup, just working with stitch points instead of attached to geometry. And then the other type of stitching is actually glue. Glue is very similar, except that instead of having one stitch per point, you can actually have multiple. So in this case, we have this kind of glue search here, and this constraints per point applies to the group we're talking about here. So instead of only getting one constraint per point that's in this group, you can actually get up to the number specified here. And so we'll see that as and this can be useful for things like gluing hair together, and anything where you want sort of a mass of constraints on a particular point to sort of hold it in place better. So please zoom out just a little bit. You can see that a lot of these points actually have multiple constraints on them now to different points between the cloth and the hair. So this piece of cloth right here is constrained to both this point on the hair and this point on the hair. And then finally, this is actually, we can look at how what the Vellum constraints DOP is actually doing internally. It's just creating new constraint primitives. So if we wanted to, we could create them ourselves. So this is actually only about this little page of VEX code. So this is a geometry wrangle. It's set up to work on the constraint geometry. So that's the geometry that holds the constraint primitives. And our inputs are the constraint geometry and then the DOP data. So these are the points themselves is going to be our second input. So this is actually, again, what's going on inside the Vellum Constraints property. Vellum Constraints property DOP and this one, which they're all just operating on these two pieces of data. So the code here, what it's going to do is it has a source group, which is going to be the cloth, and the target group, which is the hair. And so what we're doing is looking at the point that's in the geometry, the particles essentially. And if the current point in the constraint geometry is in that same group, then we want to operate on it. Otherwise, we just return out. We look up the position of the particle. We look for the nearest position, the nearest particle that is in the target group in the particles. And if it doesn't find anything, it doesn't do anything. But if it does, then it creates a polyline primitive between those two points, and then just sets all these attribute values. And these are common stiffness, damping ratio, rest length at the distance between those two positions. And then it flags this particular constraint point as being glued, and then we only use the unglued ones. So, and then we just have parameters for all these things. So this is basically doing the same thing as what this Vellum Constraints DOP is doing. It's just replicating it in sort of its own code. But if you hit play, you'll see it does the same thing. So obviously for this case, you would never need to do that. But if you come up with new and interesting ways to create constraints dynamically or in SOPs, all you're doing is creating primitives. So this is how you can do it without even going into a SOP solver. And generally, you don't need to or necessarily even want to go into a SOP solver if you can avoid it. So now I'm going to quickly just go through a few more examples of dynamic constraints. This is a pretty basic setup where we've got a sphere that we apply a mountain SOP to make it sort of noisy, and then just move it up here and turn it into fairly stiff cloth, add some velocity, and then we're going to emit a bunch of these over time. And if we look at what this simulation looks like, we've got a bunch of dynamic constraints being created as the spheres, or as these kind of noisy spheres, hit the wall. And then there's also dynamic constraints between the rocks themselves. And then some of these constraints that are attached to the wall become very stiff or even unbreakable at a certain point. So to set this up, all we're really doing is we've got one set of constraints, or one Vellum Constraints DOP, to attach the spheres to the wall. So it's using the DOP context geo 2. So this is basically looking at the third input of the DOP now, which is this grid. And again, that's the same thing being used by the static object. So they're again, this is just the collision object and the target of the attached constraints are the same. And then we've got another set of constraints that are being created between, and these are glue constraints between the rocks themselves. This is just like we had it before. They have a particular search distance, and we're making them breakable. And a compression stiffness of 0. That basically means that they can get as close as they need to together, but then there's only stiffness as they start to pull apart from one another. And these are breakable as well, obviously. And then one other thing we did with a Vellum constraint property here, just as an example, so we're operating on the attached group, and we're going to affect the break type. And basically, as soon as we go below 4 in the y-axis here, we just set the break type to none. It just turns off braking. So that's all that's happening here, is these particular attached constraints, the ones that attach the geometry to the wall, are being made unbreakable past a certain point in y. There's another way to do it. You could basically do the same thing with this Vellum constraint property, and in this case, we're doing similar to what we just did in the previous example. We're operating on any broken constraints and just overriding it if it's below a certain point. So that's kind of just a simple example of again, these kind of sticky collisions that we were looking at in the previous example, just kind of more involved because it's actually this constantly emitting geometry. And so now we're going to look at an example of creating dynamic pin constraints. So in this case, we've got just your basic circle that we've fused together at the end. If we don't do this, it's not going to be by default. This final point isn't actually fused together. So we're just fusing this together and turning it into a loop of hair. And then we're going to set some velocity and emit these over time. So if we look at the results, basically we're just sort of throwing these loops onto this collision object. And this is fairly quick, but the problem here is that as this pile of rope gets, or pile of hair, but it sort of looks like rope, gets taller, or we get more and more rope on it, you see it sort of starts to bounce and kind of jitter a lot, just because it takes a lot of solving to get these kind of lower levels to support all this weight without, in a purely sort of stable pile. So it's not bad, but it's just a little on the kind of jittery side here. So I wanted to look at a few different ways that you could fix that. One of the easiest ways is to go in here and actually create a layer point attribute. So as the vellum constraints come out of the hair, we're actually going to add a point attribute, this integer called layer, and we're just going to set it to the current frame. And what this does is this works in conjunction with the Vellum Solver's layer shock. So this is, if you've ever worked with grains, it's a similar idea. But what it does when it's solving collisions, it essentially means that layers that are higher are treated as if they weigh less than the lower layers, just for collision purposes. So if we hit play here, what that means is that each layer, and it only compares whether one particular layer is higher than the other. So as these points are coming in, because their layer is set to the current frame value, they're always at a higher layer than before. So than the lower ones, the ones that've already been emitted. So you can see we get a much more stable pile from this, which is really nice. So this is kind of a nice way of doing that, and pretty cheap and pretty, built into the solver now, which is nice. Actually, when I originally created this test, we didn't have layer shock yet for vellum. We only had it for grain. So this actually works pretty darn well. And then on top of that, we can even add auto sleeping. So if we do that, what that's going to basically do is as these points slow down, we're going to actually set their stopped attribute. And actually, I need to increase this radius a little bit so we can actually see that. And that's too much. Okay. So what's happening here is these points are actually, once they are slow enough for long enough, so below this velocity threshold for this amount of time, they're actually having their stopped attribute set to 1. So it's basically dynamically pinning them. But this is, as we talked about in the very beginning of this class, this is a permanent pin. So it's adding pins, but it's adding a hard pin. So it's basically setting that stopped attribute to 1, which imagine we can see if we look at the geometry. So things start out, nothing stopped, and then over time, just more and more of these attributes are going to be set to, more and more of the stopped attributes are going to be set as things slow down. So the only problem with this is if we go back up to the geometry level and look at the results. Actually, let's look at it here. Well, yeah, we can look at it here. We're using the Vellum post process to look at the guides. Actually, polywire might even be a better way to do it. It looks just a little unnatural because we're actually getting this, everything here just freezes in place. So there's absolutely, once it's stopped, because it's a hard pin, none of these are going to move at all. And it just looks a little bit unnatural. So what we can do instead is if we get rid of it, we can even get rid of that layer and go back and turn off auto sleep. So what we're going to do ourselves is we're going to do something kind of similar, but we're going to find all the slow points. So we're basically using that same threshold, just looking at the velocity vector and putting it into this group, this slow group. And then we're going to do a dynamic constraint, but we're going to actually do pin to target and make it a soft constraint. So it's similar to what the auto sleep is doing, but we're making a soft pin here with a very high damping ratio. So that lets us, and we could even do things like plasticity and braking and all this kind of stuff, but all we really want to do here is get a similar effect to the auto sleep, but not make it a hard pin. We want to make it a soft pin. So you can see we're creating our pins here, but as the higher up ropes fall onto the pile, the lower points, the lower ropes are actually responding a little bit. So it generally is going to look a bit more natural, especially at this level, because we get this sort of reaction within the pile. Not a lot of reaction. It's still quite stable, but you get just a little bit of bounce, and you can dial that in based on the stiffness of those dynamic constraints. So this is just kind of an interesting example of using pin constraints to kind of come up with a more stable pile of rope here. There are some other ways to do it, but this just is a way that kind of gives you more control. So this file is an example of using vellum constraints to not really dynamically, but to constrain pieces of geometry that come from different vellum source DOPs. So just to look at this real quick, it's just a file where we've got these balloons that are attached to strings, and then over time they're pinned at the bottom, and then over time the pins release and they sort of float up into the air. So the way this setup works is we've got all these lines that are going to create the balloon strings, and we just copy them around the circle, and we're creating a group for the pins here in the middle. And then we use hair constraints on the strings, and then we set pins for those points here. And this is a stopped type pin. So it's a hard pin, but it's not permanent. So, and that's how we release it later. And then we're just randomizing the rest length a little bit. So these are going to all be, these hairs are going to just be a little bit different in length, just for the look. You could also do that up here just by changing the geometry. But and then the balloons themselves are just spheres, obviously, and copied around that circle again. The tie is just the point right here where the string is going to attach to, well, really where the balloon is going to attach to the string. And then we create a cloth, just like creating the configure balloon, but this is creating a weak cloth or kind of stretchy cloth, and then with a pressure constraint. And then we're just randomizing that volume a bit. So that's some of them are going to be a little more inflated than others, basically. Then within the .NET itself, we have one vellum source that's bringing in the strings, and then one vellum source that's bringing in the balloons. And so I mentioned earlier that these actually work similar to pop emitters. They actually create streams, like pop streams. So we can put pop forces below these things and apply, and that by default, they will only apply to whatever emitter is above them. So this is all the strings, and we want drag on those strings so they kind of hang down below the balloons. And then the balloons themselves, we actually need a way for them to go upward in the sky. So we're just putting some wind on just the balloons that points upwards with a little bit of noise. And so that's why you get this kind of noisy, bouncy kind of look as they want to sort of move upwards. And then finally, here's the actual constraints. So what we're doing is we're welding the, and again, remember the cloth should go to the hair. So we're welding the tie, this point at the end of the balloons, to the hair. And we're setting, in this case, this is not dynamic. We're just saying on creation frame. So on frame 1, set up these welds. And the reason we need to do it here is there's no place that the geometry is all in one location. Like these SOPs don't know, these chains of SOPs don't know about each other. But once they come into the simulation, then we've got all the geometry here. We can actually refer to these groups and constrain them together. We don't care about any bend constraints in this case because they're really not relevant. And then finally, this is the, once we get past frame 30, we're just looking at all the currently stopped points, which will only be these pins here. And just based on some sort of random threshold, we're releasing them. So a pretty simple setup over in reality, but it gets kind of a nice look. And then finally, I just want to look at what you need to do if you want to try to actually remove some vellum geometry from a simulation. And so this is just the example. It's just some pinned cloth, and it's just basically kind of being eaten away as it goes below the y=0 axis, or y=0 plane, sorry. So all we're doing here is we're creating a group of the points we want to delete. So these are the particles it's looking at. So once it goes below 0 in y, it's putting it into this to delete group. And then we're using this vellum constraint property here. And we've set, so what we need to do is, remember we've got the constraint geometry that has all the primitives and points that have identical point numbers to the particles. And then in the the geometry itself, then we've got another point as well. So we need to remove both points and the constraint primitive as well, or any constraint primitives that reference that point. So all we're doing here is saying, look at all of the points for the particular constraint that we're looking at. If any of them are in that to delete group, then we want to remove it. And we want to remove the corresponding point that's in the constraint geometry. So this is operating on the constraint geometry. This is operating on the particle geometry. And so all it's doing is then deleting that same point in the geometry, in the particle geometry. So this removes everything from the constraint geometry. This removes everything from the particle geometry. So the point numbers are going to stay in sync, and we get this sort of nice effect of just removing everything that has to do with a particular point that we want to delete. Maybe a little more involved than it should be, but this is, if you want to remove vellum geometry, this is what you need to do. Just as long as you keep those point numbers in sync, then you should generally be okay. Our next topic is plasticity in the Vellum Solver. And so what we mean by plasticity is the solver can blend constraint rest state towards the current state when deformed past a threshold. So what that means is if you've got something like a straight piece of hair that has bend constraints on it, all of their rest state will be an angle of 0. But if you have plasticity enabled on those constraints, if it gets bent past a certain threshold, either by, say, a collision object or wind or any kind of forces, then once it's past that threshold, the solver will start to blend that rest state of 0 towards whatever the current state is. So if it's a rest angle of 0 and it's bent past, say, 5 degrees, it'll start blending that rest angle towards 0. So it might end up at, say, 2.5 or something. So once the collision object or the wind has passed by, when the hair returns to its rest state, that rest state will no longer be straight. It will be bent. And so it'll actually look like the collision object has caused this sort of permanent deformation in the geometry. So the amount of that blending is called plastic flow, or at least in Vellum it's called that. It's specified per constraint, so all these thresholds and all the different plasticity parameters are specified on a per constraint basis. And each one of those parameters can be scaled by a point attribute. Its implementation is most similar to the wire solver, which has similar parameters and a somewhat similar implementation. So the plastic flow begins whenever the constraint has exceeded the plastic threshold. And so for bend constraints, that's specified in terms of degrees. For stretch constraints like distance, that is specified in terms of either a ratio like 10%, so it'll start having plastic flow once it's stretched past 10%, or an actual just regular measurement, so say 10 centimeters. So plastic rate is the parameter that specifies the amount of flow per time step. So basically how quickly it blends from the rest state to whatever the current deformed state is. So if it has a high plastic rate, it will very quickly look like the geometry has deformed to match whatever the current state is. And if it's a low plastic rate, it'll take a while. So it can be deformed for a while and it will actually still snap back to something close to its original state. And we'll see some examples of that. And finally, plastic hardening allows the constraint to be either stiffened or weakened during that plastic flow. So that can be useful for effects like if you have a character that's going to, say, mash down a bunch of grass or something, you want the grass to look like it's been sort of stiffened and mashed together in place so that it won't then be blown around by any wind or something like that, because it's basically been hardened in the process of deforming down to that new rest state. So let's jump into Houdini and see some examples of this. So this is a simple example of using plasticity with hair, and in particular for using it for using bend plasticity. So all we're going to be modifying with the plastic flow here is the bending of all these hairs. So all we've done here is create a grid with some points on it and created a bunch of lines that are just straight. I think there's a couple of thousand hairs here. And then we've created hair from it, and we've got this enable plasticity on. And so here's that plastic threshold, which is 5 degrees, as we've specified here. Plastic rate, which is 2. And then we're actually not creating this attribute yet, so this won't have an effect yet. And then we've got a little bit of plastic hardening. So if we hit play here, we've got a bit of wind going in the Vellum Solver, and we've got this collision object moving forward, so moving through the hair. And so what we're visualizing here is actually the plastic flow. So the amount of basically the blend of that blending from the original state of straight that has occurred towards the deformed state. And so just to jump into the Vellum Solver real quick, what's happening is we've got a wind that after 72 frames stops. And the collision object has already obviously moved past the where it's going to be colliding with any hair at this point. So this is the new state. So if we hit play, we'll actually see the hairs aren't moving anymore, but they've sort of deformed to this this state that is a result of the hair here has just been blown by the wind, and you can actually sort of see what the noise looks like in the kind of parts of wind that were blowing it around. And then this part obviously has been done by the collision object itself. So you can sort of see this. And so you can see here, like in this, through this section here, even though the wind's blowing it around, the rest state is now bent through all these sections here where the collision object went through. So the best way to kind of figure out how to set these values is actually to do something like, let's just move the rate down to 0 for now. So that's effectively turning plasticity off. And instead of visualizing the amount of plastic flow, we're going to visualize the bend angle. And so if we hit play here, we'll see everywhere this is red is where plastic flow is going to start happening. And that's why you saw it in like this section up here and down here. And then of course, obviously where the collision object is, there's lots of it here. If we wanted to have these sections here, maybe not respond quite as much, we can increase our visualization so that we are looking at a max bend angle of 10. And we can see that in that case, the only place we actually exceed that threshold is where the collision object happens. So everything else, or very rarely does it actually get red. So if we want to go back to our plasticity and go back to say 2 and change our threshold to 10. Sorry, I need to change our visualization back to the plastic flow. So you'll see that we're actually not getting any plastic flow here. No permanent deformation. There's a tiny bit right at the edges here, but in general, it's all happening just in this one section where the collision object went through, because that's the only place that we're exceeding that threshold. And then if we look at it, you can see though that it's actually not deforming the collision area that much. And that's because it only deforms it past 10 degrees for just a few moments, like not very long at all. So what we would want to do is, if we want to get more plastic deformation just localized to where that collision object is, then we should increase the rate. So what will happen, say we go very high here, is as soon as it deforms, just in this collision area, it'll much more quickly move to that deformed state. So you can see that the hairs through that collision object actually will stay down, will stay deformed much more than they were before, because very quickly they move to that bent state. So it does a pretty good job of bending the hair down just where that collision object is. And then finally, if we go back to let's go back to our original settings or something close to that, we can create an attribute on these points. And so we're just doing it where we set basically everywhere on the positive z axis to 0, and everything over here is 1. And then we're scaling the plastic rate by that. And so the effect of this will be to make it so that there's actually no plastic flow that happens in this section here, because we've scaled that rate to 0. And so any plasticity that's going to occur will only be in that section where we have that attribute set to 1. And so you can see that's limiting the areas that the plasticity can happen. So that's an example with hair, and in general, plasticity works really well with hair. In part because it's pretty easy to make very stiff hair. There's usually only there's not that many points in a lot of there's 10 points here, and the constraints for hair can work pretty well to be stiff. They're really only operating along this one dimension here. It's a little tougher to get really stiff cloth to do things like bending metal or something like that. In fact, with vellum, it's quite difficult to get high res or even medium res, really stiff cloth. So we'll look at how you would do something similar to this with cloth, but just be warned that it's a little tough to do at anything approaching sort of production resolutions. So here's an example with cloth, and as you can see, it's quite low resolution, and we've actually we're even cheating it a little more by turning gravity off at the beginning. But if we hit play here, and we've pinned the edges over here, so we'll see as we move up, again, we're doing bend plasticity here. So we'll see that we're getting this bending, this plastic bending through or plastic flow through all this section. And then after a certain point, we disable those pins, those are just stopped pins, and let the cloth fall down, and you'll see that it's now, its state is now this deformed state. So it's sort of acting like bent metal or something. We're actually using Vellum post-process both to visualize it and to subdivide it once. So what this looks like is it bends up, and then it just drops down like that into its now bent state. And if we go into the solver, this is again the SOP solver, the SOP version of the Vellum Solver. So we're doing a few things here. We are at frame 40, we're basically turning off plasticity. So we're turning off, for all of those bend constraints, we're setting their plastic rate to 0. So once frame 40 is when it starts to fall. So we want to turn off plasticity at that point so that everything that happens in this sort of rocking back and forth doesn't cause any more plasticity or any more plastic flow. This removes the pins. So we're just doing using a pop wrangle to set that stop to 0. So we've seen that before. And then the other thing is we don't have any gravity on it. So we're turning gravity on at the same time. So that just makes it so that it's not like bending down at the beginning or anything, and just bending down or just falling down when we have also removed the pins. So, as I said, this is, if you're going to do these types of effects with vellum, it tends to really need to be pretty low resolution cloth for it to work. But, you can then do things like take it and use it to maybe point deform or somehow deform higher resolution geometry. But all the ideas for how the plasticity works are very similar to hair. Finally, I wanted to talk about soft bodies and grains in vellum. There are 3 types of soft body typically simulated with vellum, and the first 2 have a shelf tool or a tab network tool that can help you set these up. And the first one is called Vellum Configure Soft Body, and that sets up 2 vellum constraint SOPs. The first one just creates cloth for the external surface of the soft body with struts, which are basically like springs that are internal to the soft body and keep the overall structure of the soft body. And you can make them sort of bouncy springs if you want for a soft body type effect. The second one is the Vellum Configure Balloon tool, which again uses cloth for the external surface. In this case, it's often pretty stretchy cloth because you want it to act sort of like a balloon, and then the pressure constraint will maintain the overall volume of the enclosed soft body. And you can do things like increase or decrease the rest length on that pressure constraint to mimic like inflation and deflation effects. And then the final type, we don't have a tool for at the moment, but I wanted to just show how you set it up quickly, which is to actually tetrahedralize the soft body. And then you can use the tetrahedral volume constraint to make the tetrahedra maintain their volume, and then use the distance along edges. So basically put sort of springs, again, kind of soft springs along each tetrahedral edge to keep the soft body from deforming too much, even while the volume is being maintained. So we'll look at an example of setting that up. And especially in that last case, the typical way, or really the best way to work with soft bodies is often to simplify the geometry that you're going to be simulating with and try to get a very uniform, say triangular mesh, and then use either like the point deform or cloth deform workflow to deform the actual render geometry before rendering. And that's just because a lot of the times the way that your render geometry is modeled, you'll have very small polygons in particular areas that are just to make it look right. But in general, for a simulation, you want a much more uniform mesh if you can do it. So we'll look at an easy way to create that. Then finally, we'll talk about grains, which are similar to the grain solver that's been around for a while. So we're not going to spend too much time on them. They generally need additional substeps versus the one that comes as the default for vellum. And then I just wanted to show a quick setup using grains plus some breakable glue constraints and attached to geometry constraints, which can give some interesting effects. So let's jump into Houdini and look at that. I wanted to start out with a pretty basic inflatable balloon type simulation. And so here we're just going to take all these different copies of Flip here, and we're going to inflate them over time. Here, I'll hit play. I've already cast this out to disk. And this object comes down and squishes them, and then lets it up, and then at the end they deflate. So the way we set this up is we're taking the this flip test geometry, and as we can see, this is where, like this area here, when we're doing soft bodies or even cloth, really most kinds of simulation, this area here is not going to be very friendly, for instance, with our simulation, because it's got all these tightly sort of squeezed together polygons and lots of points right in this area. So we want to generally have a more uniform mesh if we can when we're doing simulation. So we're going to first Boolean it, which is going to just sort of, because these are separate pieces of geometry, like the legs are separate from the body, we're going to Boolean it so that they all become one piece of geometry. Then we polyreduce it, and we're going to actually remesh on top of that. Then you can see we get this nice even mesh that's going to be really nice for simulation and simulation for soft bodies. It's also lower resolution, which means it'll be a lot faster than if we'd tried to work with the render mesh. And so then we've just got reference copies here. So we've got a copy that just does a copy and transform here to create a bunch of copies of the simulation data. And then we reference copy that over here, and we do the same thing with the render geometry. And again, we do the same thing for color. Then over here, we're actually setting up the soft body. So we have the cloth, which is kind of stretchy, not too stretchy. These two are equivalent to basically the Vellum configure balloon shelf tool. And then this pressure constraint. And we are putting it into an output group called inflation. And then when we go into the Vellum Solver, we actually have this Vellum constraint property that we've looked at several times before, but we are just coming up with a random scaling of the rest length scale. So basically the rest length would, in this case, is the initial volume of these guys. And then we've got this animated pressure that we're multiplying it by. So it's just going to animate to a real high value to inflate everything. And then over time, eventually it's going to animate down to a low value. So it starts out, it goes up to 10 pretty quickly, and then it drops off to 0. We're actually clamping it at 0.5 here with this max. But so then each different pressure constraint will get scaled to some value between 0.5 and 2. So a pretty basic setup, really mostly interesting because of the just of this workflow for deforming the render geometry. So then I've cashed it out with a Vellum IO SOP here. And I don't know if we've looked at this, but one of the nice things about Vellum post-process is it'll actually let us look at all things like stress and everything on cached out values, because it's got this same visualization here. So we can look at sort of the stress and how it increases by a huge amount as the soft body gets pressed down underneath the collision object. And then finally, we are time shifting the first frame of the Vellum of the cached simulation. We're doing a cloth capture here. We could also do this with point deform, and to be honest, I'm not entirely sure. I remember why we did cloth capture here and not point deform, or because they both should work similarly. And then we do a cloth deform. So what this is doing is it's basically deforming the render geometry to match the per frame output coming from the Vellum solver, from the cached written to file simulation data. And then finally, we are transferring velocity over so that we get point velocities on each one of these high-res render geometry, and then we're subdividing. And actually, for something like this, it turns out that it can often be faster, especially if you're using geometry attribute velocity blur like this, to subdivide in Houdini and not subdivide at the mantra level. So that's actually what we're doing here. And the result of this looks like this. So we can see we have the full res geometry here, even though our simulation geometry is much lower. But you can't, once it's simulated and deformed at right before rendering, you really can't tell that it wasn't simulated at this full high res. So this is a pretty common workflow and generally a good way of working with both cloth, but especially working with things like soft bodies. So let's look at a couple of examples of other types of soft bodies. So this is a basic example that shows the different types of soft bodies all in one file. It's really pretty simple overall, but it looks a little more complicated just because we've got the different ways of setting up the soft body all demonstrated here in one file. But the general idea of the simulation is we have these three tori. Everywhere that's red, they have plasticity enabled, and everywhere that they the other areas they don't have plasticity enabled. So you can see they all work like soft bodies here, but they'll actually get sort of permanently deformed wherever the plasticity is. So there's just an example of sort of setting up the soft bodies and showing that you can actually do plasticity with soft bodies as well to get this kind of permanent deformation. So this is actually this is actually showing the pressure constraint. So this is like a deformable balloon. So it's essentially, and you can sort of see that as it presses out here, you get this sort of inflation effect along these outer parts where it's trying to maintain the overall volume of the soft body. But we're actually making, so here's the cloth again, which is stretchy, and the pressure. We also have plasticity enabled on the pressure constraint. So it's actually deflating a little bit due to being pushed down like this. And then finally, we're just using a vellum pack, which is just, again, just an easy way to put the geometry and the constraints into one piece of pack geometry. So we only have to use one switch here. So this is as if you did the vellum configure balloon tool. This one is if you did the soft body. So if we look inside these, you'll see these are the struts that are created. And so these just act like internal springs. But again, we have things like we can have plasticity enabled here. So you again get a sort of soft body with permanent deformation. And so we can actually look at, I've play blasted all these different examples out. So this is the struts example. You can see they're a little more rigid. They don't have quite as good volume preservation. Like it doesn't really sort of look like an expanding balloon because there's nothing to maintain the overall volume. It's just those local struts. And again, you can get this deformation. So the struts across here, for example, deform a little bit when it first hits here, and then even further as you squeeze it down. And then the next approach is this is actually the tetrahedral one. So what we're doing here is we're going to actually do this solid conform, which is a good way to create the tetrahedral representation. So we see we've got all these internal tets that are going to be used for the simulation. And we've actually got this add surface triangles option enabled. And what that means is that not only do we have these internal tets, but we also have triangles that are along this surface everywhere. And we're actually not going to use them in the first case, but we'll look at a case where we actually do use these. In particular, they're useful for making bend constraints along the surface. So if you want to have the surface actually have a bit of bendiness or stiffness along the each triangle edge, you can actually do that by adding these surface triangles and then having a separate vellum constraints that just does bend across triangles. But for the moment, we're just going to do distance along edges for this one. So what this will do is that I'll actually create each one of these tetrahedral edges will turn into a spring. And in this case, a fairly soft spring. And again, with plasticity enabled. And then we've got, I'm sorry, I'm looking at the wrong one. Then we've got tetrahedral volume ones here. And so these are very strong. So what we want this to do is basically when you do this combination, the springs along the tetrahedral edges are how much the soft body will deform. So how much it'll sort of maintain its overall shape, how soft or stretchy it looks versus how rigid it will look. And the volume constraint, the tetrahedral volume constraints are just maintaining volume. So you can have something that looks like can maybe squeeze down like a pancake, but it'll automatically bounce back up because of these tetrahedral volume constraints. So you can generally think of distance as being deformation and tet volume as being volume preservation. And then we do the same thing with packing that together. And then the result is this one. And then it ends up looking a bit more organic So you can sort of see you get this local volume preservation. So it doesn't look as much like a balloon as like sort of organic flesh or something. As you see, it's kind of maintaining volume around here. But again, we can have the plasticity so that it ends up with this kind of permanently deformed and loss of volume along the collision object here. And so again, it gives this kind of more more sort of organic sort of flesh or tissue type look, which can be kind of useful. And then finally, and so these are the three main examples I want to give. But if you take this tetrahedral example to sort of its extreme, you can actually make these tetrahedral edges internally very stiff. And then they actually start to act sort of like these struts that we looked at before. So again, that would just give you an object with very stiff strings internally. So another way to create soft bodies that are actually a little more rigid is to create a very strong springs internally, or actually they're not that strong, but pretty strong strings internally, and then actually use those, create those bend across triangles constraint on that surface triangle group. So what we're having is a combination of fairly stiff springs inside the object along with bend constraints on the surface of the object on these surface triangles. And then with plasticity in both those cases as well. And so what that looks like is this, and you can see it's a bit more rigid actually, and looks more like a sort of hard shell kind of object, and that's from the bend constraints that are along the surface triangles. And again, all of this is just going through a point deform on the original tori here, which when we're using the things like struts and the pressure constraint really isn't required, but when we're doing things like tetrahedralizing it really is. So just in this case, we're going, in all cases, we're going through this point deform and then subdividing at the end. So that's all I wanted to show about soft bodies. Pretty simple, but there are a few different ways to create the soft bodies, and they all sort of have different properties. So it's worth playing around with the different setups here. Finally, we'll look at a grain example, and this is again fairly straightforward. I just wanted to show how you can use vellum constraints on top of grains. So we're starting out with another torus and creating grains from them using the vellum configure grain SOP here. And then we're going to use the cluster SOP to actually create a bunch of different sort of clusters within this point cloud here. And the reason we're doing this is because when we actually we're going to glue these grains back together again. When we work with glue, we've actually got this cluster attribute. And what this means is the glue will actually only look at other points within the same cluster. So when we have these clusters, and then we're gluing them together, we're basically gluing these different clusters to themselves, only to points within the same cluster. So we're basically creating these sort of a bunch of different pieces of this grain geometry here. And you can actually see that if we do an exploded view here on just the constraints themselves. So these are all the glue constraints. So we've basically created a bunch of different pieces with these glue constraints between only the grains within those pieces. And these are not terribly stiff. They're stiffness 1,000, so they're kind of soft springs. And then we're creating a bunch of constraints per point. So each grain can point at a bunch of, can be configured to a bunch of other points around it. The other thing we need to be careful about here is normally this group type isn't quite so important. So you can normally leave this group type as like primitives. The problem is that we don't have any primitives. We only have points here. So if you set this to primitives, basically all the constraints go away, because it's trying to create a group out of all the primitives and then use the points in those primitives, but we don't have any primitives. So if you're doing constraints on grains, you need to make sure you set this to points. And you can leave this part blank in both cases. And then finally, we've got just some detach object chance, just means sort of the chance that a particular grain won't be attached to from another grain. So we'll get sort of falling off grains within these pieces, which can be an interesting look. And then finally, we created just a scale from across the Y part of the grains to basically make the glue weaker as you go towards the top. And then we're using a scale by attribute to control that. And then we've got some pins across the top here. and they're pointing at this target geometry, which is just a really simply animated version of the grains over here. So if we look at what that looks like, the grains are falling down, and then they're sort of sticking together on their particular pieces, and then the pins are actually holding this part up, and they move apart, and then these constraints break because we set the breaking here. And so then the other thing we can do that's kind of interesting, we can actually get a little bit of a like viscoelastic fluid look by just surfacing this. It looks a little bit like, I don't know, shaving cream or something. But if we look at that in real time, this is just going through and showing the simulation and then the visualization with all the glue constraints. And then finally the surfaced version. This is all those glue constraints. And we can see as they're getting red here as they're about to break. And they break as we move forward. And again, it gets a little easier to tell that these are really separate pieces of grains that are done per cluster. Then if we wanted to, we could do things like add a attach to geometry constraint, so have it fall down on this grid. And so just use a Vellum constraints DOP in here set to each frame. Again, make sure that we set the group type to points and then reference that same geometry, and creates, you know, soft breakable attach constraints. And we'll see we're getting those here. You can see these are the attached to geometry constraints. All these grains are actually getting attached to this collision object here, and they're sort of sliding down, but they're breaking as well. So all this shows is just that the grains can be a lot of these like sticky collision effects and you know, breaking up pieces and that sort of thing can all, if you set up the constraints the right way, can all be used in a similar way to what we looked at with regular geometry. All these same sort of techniques apply, which can lead to some nice effects. Anyway, this has been a very long class. Thank you for your attention and for listening. All of these example files will be available, and so I hope they're very useful to you. Thanks very much.